o'clock Singapore time. It's 8 o'clock morning in Norway. Welcome to the fourth day of the Norway Singapore Science Week. And we are into the third or the second of three thematic areas. This webinar and the two following webinars on Tuesday and Wednesday will be on decarbonization. And this first webinar, which I'm honored to be allowed to be moderating, is on energy efficiency and energy recovery in industry and utility scale systems. My name is Per Christer. I'm a science and technology counselor at the Norwegian Embassy in Singapore, and I'm very pleased to welcome all of you for this webinar. We have a very tight program today, very exciting and very tight. I will show this here. Let me just get this one right. This is the detailed program. So without further ado, I would like to introduce the two co-chairs, Professor Iftekar Karimi and also Professor Truls Gundersen. And Truls, maybe you can open with giving us some welcoming and introductory remarks. I give the word over to you, Truls.
Yeah, thank you, Per Christer. I'm very happy to welcome you all to Professor Karimi and I, with a lot of help from Per Christer, have put together. We have 8 presentations. Resource efficiency is and will be very important in the future, whether it's water, food, or energy. And I guess in Singapore, even space efficiency is important. So our session on energy efficiency handles a very important topic, even if we change from fossil to renewables. So without further ado, I would like to give the word back to Per Christer. Thank you.
Thank you very much, Truls. I'd like to inform that we are recording this session, and we will share the recordings with the participants later on YouTube and also the presentations. I'd like to continue the program, and I'd like to hand the word over to Professor Iftekar Karimi from the National University of Singapore to talk about industrial energy integration and recovery in Singapore. So with that, Professor Karimi, please share the screen. I will unshare mine and start your presentation.
Let me try. Okay. Does it look okay?
This looks very good. This looks very good.
Okay, wonderful. Okay, good afternoon, everybody. It's a pleasure to be here. I think we have an exciting session. And since the time is limited, I'm going to turn on my stopwatch so that I can keep track of my time. Okay, I'm going to talk about industrial energy integration and recovery. Although we have inserted this word Singapore, but obviously whatever I talk about is not only relevant to Singapore, but also relevant to the chemical industry in general and other similar industries. All right. So I'm Iftekar Karimi from NUS. I'm from Department of Chemical and Biomedical Engineering. As Truls started, energy conservation is obviously very essential, and especially industrial energy consumption is also conservation is also very essential. I think the usual suspects, I think we are all familiar with: rising energy demand, fossil fuels, climate change, carbon emissions, etc. I think the key thing about industrial energy is this: that industry is the largest consumer of global energy, and it's more than 50% of the total energy, primary energy consumption at most places. In fact, for Singapore, it's like 60% in 2020. chemical industry in particular is notorious in the sense that it requires extreme conditions of processes, in the sense that extreme temperatures, either high or either low, right? No matter which way you go, you have to expend energy. So these are all very energy intensive operations, and chemicals and petroleum refining, which is the dominant industry sector in Singapore, consumed almost 76% of Singapore's industrial energy consumption. So that's really says a lot in terms of the importance of these. And if you go to, if you ask any refinery or other chemical industries companies, they will say that their annual utility bill can run into thousands of dollars, even dollars. So it is energy. That's no wonder that chemical industry is the pioneer, right? Was the pioneer in energy integration, and then the whole thing started when let me see. Yeah, the whole thing started in 1970 when the oil crisis happened. But I think if you ask no in the industry and you can say that, okay, what has made impact? Sometimes we think that things that happen in academia don't necessarily go into the industry, but these are two classic examples. Process simulation and process integration or energy integration have made real impact on chemical processes. So it is very important for us to look at that. And what has happened now is that because of the global concerns nowadays, there has been a renewed interest in energy integration. This has been a topic which has been studied since 1970, so it is quite mature in some sense, but we were surprised to find that there are still a lot of opportunity, and I will discuss some of them later on. Let's see if I can move this slide. Okay, all right. So what is my objective? So what I want to do is I want to basically give you an idea of what heat integration means, what heat exchange network synthesis means. I'll discuss, give you an introduction to two popular methods which are used for heat integration problems. Pinch analysis is the household word in heat integration, and mathematical programming is sort of the newcomer, which has a lot of potential. I'm also going to describe a little bit of work, just give you an introduction. I promise you there's no more than one intimidating slide in my presentation, all right, which has any mathematical notations. So we have done some work to advance the frontiers, and as I said, there are certain novel areas, extensions, for example, interplant heat exchange, work exchange, which are important advances in this field. I would like to acknowledge support from lots of funding agencies, NUS in particular, Energy Market Authority of Singapore, ExxonMobil, Singapore Energy Center. My interest basically began in this topic when I visited Qatar University in 2004, and we looked at the LNG plant, and we found out that there was a lot of opportunities for heat integration. And so Qatar Gas, that was the first project that I started working on it, and then I have been into gas and I have been into energy integration since then. Lots of people I have worked with. Prof. Gundersen, who is a veteran in this field, he's been working in this area since a long time ago when this thing started. Prof. Camel from Waterloo, I had some, and Prof. Linga, I'm working with him as well on some energy integration problems local to Singapore. And I have obviously several students and research associates have worked with me as well. All right. So the classical heat integration problem, right, is being stated as follows. I mean, this is like a lot of variants have developed over the years, and this is no longer the problem, but the problem still is real, right? So basically, what you have is some cold streams which need to be heated, some hot streams which need to be cold, and you are given the target temperatures. And what you want to do is you want to find out, okay, first of all, how much utilities would I need, right? Is there a possible exchange which happens between hot and cold streams? I can transfer heat from hot stream to cold stream, and that way I can save the utility. So one important question is, okay, how much external utility I would need, right? Second important question would be that what sort of exchange network I would design so that I can maximize the heat recovery and minimize my cost. So pinch analysis was the first method that was developed, right? And again, it's a buzzword in the industry, right? Most people know, most people who are in industry know pinch analysis. it was basically a graphical method where you draw some sort of composite curves, cumulative heat demand curves, and then you try to match them together to maximize the or maximize the energy synergy between them. And what you get is a pinch which is limited by the thermodynamic driving force of temperature differences. Right, so that way you can find out what is the minimum cooling load required and what is the minimum heating load required. And then, so the pinch analysis basically is a sequential method, right? It breaks up the problem. It's a decomposition method. It breaks up the problems into one, which is the targeting problem. So that means you determine the utility requirements, and then based on the target, you then try to develop a network which sort of maximizes the heat recovery so that you can reach target of utilities. Now, I think pretty soon when this thing started, right? Basically, people realized that if I could express this optimize entire problem into one problem, and if I could use an optimization method, I could get all the answers in one shot. So that's basically led to the idea of mathematical programming, which sort of is an integrated method of looking at all the questions and giving all the answers in one shot. And one of the differences between the two methods has been that mathematical programming has been more of cost based. And of course it can be used energy based as well, but it was primarily designed for cost based objectives. And what you something called superstructure, which is you try to include all possible combinations of heat exchanges into a graphic, into a process structure, which you then solve as an optimization problem, so that what happens is that things that are not so good get dropped out of your superstructure, and then what you get is a net structure, which is the best structure for your heat integration. All right, okay. So as I said, right, superstructure is the key, right? It defines all the admissible network configurations. If you miss out on a degree of freedom, then what happens is that you miss out on some particular possible configurations, and then you get inferior solutions. Okay. I think I have lost my stopwatch. Okay, stopwatch is working. All right, fine. Okay, all right. So there are two classical workhorses for superstructure which were developed back in 80s. But there are some limitations of these superstructures, right? So they miss out on some configurations, and also a key aspect is that they are not readily extendable to address the retrofit problems. And I think you can realize that most plants exist, and lots of them have heat integration opportunities. So retrofit problem is a very important problem. And so we need something which would be able to address both grassroots as well as retrofit problems seamlessly. Right. So I think that was one of the motivations which led us to come up with a novel superstructure. Which is basically exchanger-centric superstructure. The two superstructures that I mentioned here, one was match-centric. That means you try to see, okay, what are the possible exchanges, matches between streams possible? And then the other superstructure is called stage-centric, where it divides the evolution of temperature for every stream into segments or stages, and then it tries to look at the possible combinations. So what we did was basically, instead of looking at it as a stage or as a match, we look at it as a pool of exchangers. So we are saying that, look, heat exchanger network is really basically a bunch of exchangers, right? And I have to have, I'm going to assign streams to that. So instead of looking at a match, instead of looking at a stage, what we do is we look at exchanger and see, okay, what stream should I assign? So obviously I should assign one hot stream, I should assign one cold stream. But in a superstructure, I say, okay, I'm going to assign all the streams and let the optimizer decide which stream is the best combination to assign, right? So basically what we come up with is nonlinear model, right, which basically selects the exchangers and also assigns the streams to minimize the total cost of network. So that's basically it's a very flexible superstructure. It takes care of the limitations of all the other previous superstructures, and it gives you a solution. So clearly it's not an easy problem to solve. So we developed an algorithm to solve the problem also, and we showed this on 3 literature case studies, especially, and you don't need to probably go into all the details, but needless to say that, suffice to say that we've been able to get better solutions on all the 3 case studies, especially on the first one, which involved a lot of utility usage. We were able to save around 66% of the TSE, the total analyzed cost. And we also found a solution which is better than the so-called global solution reported in the literature. Okay. All right, so I think this is, I think, a significant advance in terms of the classical heat exchange network problem. So there are 2 advances. Is the power infrastructure. The second is an algorithm for solving the optimization problem. All right, now clearly, most of the focus, especially on heat exchanger problems, was intra-plant exchange networks, right? That means you look at, because the processes are nearby, you can exchange heat with them. So you assess, and okay, what is the extent of integration that is possible? But clearly you can go beyond this, and then you can say, okay, if you have a chemical cluster, for example, and you want to and so, for example, Jurong Island is a cluster, right? And Jurong Island has can also, plants inside Jurong Island can offer synergies. So what we did was we also extended our methodology to address this problem, and we are still working on this one. But there are lots of issues and challenges. So first of all, the first issue is that all these exchangers, where should they be located? Right? I mean, should they be in the plant? Should they be in some other place? How about transporting? So if you have to transport a stream which has hot stream or cold stream from one plant to another plant, how do you take care of the logistics? What about the costs of piping, etc. So exchanger ownership, right? If the exchanger is located at a plant, right, and then you send a stream to that plant, okay, how about the ownership? If exchanger is not located there, if it is located somewhere else, who takes the ownership, who takes the custody? And so what is the incentive for collaboration? Why should people collaborate? Right? What is the incentive for them? How do you ensure operational dependence? Because your operation is now tied with somebody else's operation. Something goes wrong, you get affected as well. So all of these are very pertinent questions. How do you share expenses? What about the pressure losses in the pipeline? What about heat gains and losses? What about if you want to use heat exchanger fluid that circulates through the plants? What about the cost of piping, etc.? So there is a number of challenges that are sort of different from the classical heat integration problem that people have addressed. So we looked at we have developed formulations and procedures for, if you were to look at all your exchanges at a central facility, and then you send streams back and forth, right, to make them heat exchange here. And this is something that could be, for example, managed by 3PL or something like that. Or it could be another possibility where you have enterprises, and then you locate stream exchanges at those enterprises, and then you send streams from one end. So this is a more flexible way of looking at constructing the network. Then we also looked at the net present value of all of this adventure. And then what we made is that maybe the incentive for each coordinate, each participant to be willing to take part in this will be that if I ensure that our rate of return is the same for each stakeholder, so proportional to the savings that they get, they also make an investment. So we use NPV as the objective function. We take care of utility expenditures, piping, maintenance, etc., and capex expenses, and then we come up with a what happened? Recording, something went wrong. Your presentation ended. Someone else has started sharing. Oops.
No, I don't think. Well, we don't see that. We
Oh,
just
you don't see it,
it.
is it?
No. So please start sharing again.
Okay, start sharing again. All right, sorry. You boy. Start sharing again. Mm-hmm. Okay. All right. Yep. All right. Okay. So basically, so we did a case study, It's a simple case study, right? Obviously, but one could look, the methodology is general. One could look at a very real case study as well, which we are trying to identify. So if you have 3 plants and several streams at each plant, we found out that you can compare distributed versus centralized HEN. This HEN will have a central location for exchangers, and no surprise that well, in this particular case, no exchanger was located at the center site. Transport costs limited the exchanges. So what happened was that the utility savings that you get in the distributed system is less than the centralized system, but the cost of transport, etc., outweighs the cost of utilities, etc. And so you get you distributed heat exchanger network system comes out to be better from an overall cost perspective. So that that methodology, right, can be used for in practice as well. So second extension that I talked about is that extension of heat exchange to work exchange. I mean, we all know, right? Work costs more than heat, right? Heating is cheaper than pressurizing. So electricity. So how can we? So this is an idea which was explored several maybe I think 10-15 years ago at University of Michigan, where they tried to say, okay, if I have a high pressure stream and I want to depressurize it, I can run a turbine, right? Like just like you do, you can use steam, high pressure steam, and run a turbine and get energy and transfer that to run a compressor. So the same idea, instead of using steam and compressor, what if I use a high pressure stream and a low pressure stream? So I transfer energy from the high pressure stream to low pressure stream. So there are obvious analogies between heat exchange and work exchange. In heat exchange, you are dealing with temperature changes. In work exchange, you are dealing with pressure changes. And then you can also draw corresponding analogies between streams and utilities, etc., etc. So the idea is, so one other way of transferring work is basically having a common shaft. And this is used in the industry and LNG industry, for example. This is called turbo expander, turbo compressor, and you can transfer the energy from one from the turbine to the compressor. So we extended, right? So we looked at the work available. This is something that I did with Prof. Gundersen, and then we published a paper on this as well to see how we can classify all the work that is available on work heat exchange. And so 10 years ago, so Prof. Gundersen started working on it, and his idea was to basically, how can we use work to enhance heat exchange? So that falls under the category of WHEN. Then a few years later, we looked at the use of single shaft to transfer work. So there we are talking about actually work exchange in a literal sense. And so if you put all of that together, what you get is a heat and work exchange network. And so this classification, it provides us a good framework within which we can develop our solutions.
Two more minutes, Professor Karimi.
Okay, I'm almost there, right? So we applied this on a practical system. We all know propylene-propane separation is one of the most capital extensive simulation, and because propane and propylene boil very closely. And so we are trying to develop this methodology, but at least we tried out on this problem, and we said that, look, if I just take a distillation column with fixed feed and products, what is the best way of integrating this feed and stage? So oopsie doops. Okay, I have a slide which I have modified and I forgot to delete. Anyway, okay. So we looked at 3 cases where we looked at, if I do only heat integration, this is what I get. So my total cost is like 5.5 million. If I do a work and heat integration, but with predefined stream identities, that means I designate some streams as hot streams, designate some streams as cold streams, some streams as high pressure streams and things like that, so that they cannot change identity. Then I get about 1.228. But if I make things very flexible, that means I don't impose any condition on my stream. So stream can actually go down in temperature. That means it's a hot fluid. Then it actually get heated in temperature. So it becomes a cold fluid. So if I allow all that flexibility, then what I get is a total cost of $1.136 million per year. So you can achieve substantial savings by this this work and heat exchange techniques. So this is again, intra process, but we can extend this to inter plant as well. All right. Okay. So to conclude, I think many of work heat integration is now a growing field. A lot of people are interested, and Prof. Gundersen has published a number of papers, review papers on this. We believe that this can offer really very good novel solutions. Because I wanted to always derive have a procedure which will derive me the refrigeration cycle or the best cooling cycle, and I can do that automatically by using the methodology that we have developed. Right. So significant advances we have made at NUS in terms of superstructure formulations, use of mathematical programming, and even we can solve large problems. And we are working on the interplant exchange problem as well, and work exchange. We have developed this work exchange framework, which also include liquid phases for the first time. And as I said, we demonstrated that if I use this on C3 splitter, we can get an oil process. And we confirmed that using a separate work and simulation as well. Okay, so thank you very much for your attention.
Thank you very much, Professor Karimi, and thank you for being on time as well. Very interesting. Please, everyone, put your questions or comments in the chat box. We'll go on to the next speaker, Professor Alessandro Romagnoli. So, Alessandro, can you share your screen and give the presentation, please?
All right. So, hello, can you hear me well?
Yeah, we can hear you, and we can see your presentation well as well. If you put it in full screen, maybe. There you go. Perfect. Thank you.
So good afternoon, everybody. I mean, my name is Alessandro Romagnoli. I'm an associate prof at NTNU. The title of my presentation today is about waste heat and waste coal energy recovery for improved energy efficiency in the energy sector. So I would like to start with this slide on the cold economy. This cold economy, the definition of the cold economy, actually, let me do point interruption. The definition of this cold economy is here, is the business and environmental value created by the efficient integration of coal into the wider energy system. And basically, the cold economy refers to how we make, store, move, and use and manage coal. It's not just referring to the coal supply chain. And this sort of concept was revamped by the University of Birmingham in early 2010s. And then when I came to NTNU, I wanted to see whether there is an opportunity to, carry out a study on the cold economy for Singapore. Now I'm doing this under the Surbana, Jurong, and NTNU corporate lab. So why cold economy study for Singapore? I mean, the cooling degree is, expected to increase by 12% in 2040, as well as there are a number of industries that are growing in scale, which require a lot of power and cooling, for instance, data centers. And then, I mean, also Singapore presents, it's not a mega city by definition, but I mean, the population is meant to grow with a higher cooling demand. And also Singapore being a developed economy, might represent, an example for neighboring countries or neighboring big cities that eventually might develop at the same rate stage as Singapore over the next few years. And then one aspect, of course, that everybody knows about is the availability of LNG, and therefore the opportunity to recover some of this LNG cold energy coming from the regasification of the liquefied natural gas. So if we look at the demand of cooling in Southeast Asia, this is basically for space cooling. You can see this is the trend as reported by the International Energy Agencies. This is where we are now. And in a similar fashion, we are trying to estimate which is the cooling and refrigeration demand for Singapore to sort of create a baseline, develop some forecast, and eventually study some scenario on how best we can meet this cooling and refrigeration demand. And actually, the reason why we are doing that is because we couldn't find any publicly available resource that tries to break down the cooling and refrigeration demand for Singapore. So we started with a data collection of different main sectors: households, industry, commerce, and services, and transport. And then for some of these, we also look at the subsectors. So for each one of these, we try to estimate which is the cooling and refrigeration demand. The approach that we follow is a top-down approach, and we have to basically, go through a lot of documented resources coming from official record, published studies, and trying to validate the information and the calculation that we came across. And this is basically what we could find out. I mean, this is the first time actually we are presenting this data. So I think the numbers are evolving, and indeed, you know, we are more than open and welcome someone who might want to collaborate with us on this exercise. But you can see that over the past 10 years, you can see a constant increase in cooling and refrigeration demand, about 30% increase over the past 10 years, and roughly 20% of the electricity consumption in Singapore goes for cooling and refrigeration. This accounts for roughly 7% of the total electricity demand in Southeast Asia for what it concerns the cooling. And this number here about fuel is mainly related with the road transport, trying to estimate how much of this fuel goes into cooling of the vehicles. So now we've done the estimate. As I said earlier, we want to project, looking at all the different subsectors, and eventually study on how best we can meet this cooling and refrigeration demand, looking at opportunities or scenarios offered by low carbon fuels, renewables. You know, now there is hydrogen also into the picture. Electromobility might be another driver, and also novel technology like for power generation or for storage. So I mean, this I can probably skip quickly on that. Everybody knows how much is the LNG available in Singapore, and this slide over here shows which are the industrial sectors that need cold at a different temperature level. Of course, I mean, LNG is stored at minus 160 degrees C, so industrial sectors that have to operate at very deep temperature, they would be better suited to use this LNG coal. But of course, the lowest we go, I mean, the lowest is the extent and the capacity of some of these industrial sectors that might need that level of coal. So when we look at LNG, more or less 2% of the overall energy content in natural gas from the cold energy. The remainder is chemical energy. And if you want to sort of position some of the technology which entirely, make use of the chemical energy or for power generation, or that produce or make use of the cold energy for cold generation. So this is, and also we try to allocate them based on the TRL. Again, this is just a very qualitative sort of chart. But here you can see that this is a more established technology with something that is coming along the way, like the alarm cycle. I will talk about the supercritical CO2 cycles, and also fuel cells that there are different types at different TRL level. And also when we look at the technologies which basically are devoted to produce cold or make use of the cold, and make use of the cold energy, these are some of the industry and application that can leverage on the LNG coal. And then of course there is some that we try to put in between, which means like if you look at CCGT, make use of the LNG coal to pre-cool the air at the inlet of the gas turbines, and the ORC, organic Rankine cycle, the leverage on board on the heat coming from a combustion process, for instance, and they can use the cold energy as a heat sink. And the same it goes for liquid air energy storage, which is a new form of thermomechanical storage, which I'll describe later on. So, I mean, where we start from, this is typically regasification process with gas going into CCGT. There is some waste heat that can be recovered to generate chill water, for instance, or electricity through a closed power cycles. And some of the LNG coal regasification could be used, as I mentioned earlier, for air pre-cooling, or also as a heat sink, or for direct utilization to the end user. So we took a baseline looking at the CCGT with no waste coal energy recovery, no waste heat recovery. We took it as our baseline, and then we start to look at different level of integration for heat and cold energy recovery. So we look at CCGT plus organic Rankine cycle, or CCGT with inlet air pre-cool using LNG coal. But of course, I mean, probably the best option that we could be considered could also be considered to couple the CCGT with an absorption chiller, and make use of use some of the chill water from the absorption chiller to pre-cool the inlet air of the gas turbine, and then use the LNG coal for some of these sectors applications over here. So we're trying to estimate again what it could be the so-called overall profit that we could achieve with these different levels of integration by considering either how much more power could be generated, or for instance, when it comes to absorption chiller, which could be the energy saving, the electricity could be saved if we had to generate the same amount of chill water that we are generating with absorption chiller via a traditional vapor compression chiller. So you can see that here we don't see much of any of a contribution. It's still something, of course, and meaningful, but really the most of the so-called profit come from the absorption chiller and chill water generation. And then, of course, when we go to the different applications, the lower we go in temperature, like deep freezing, and the best energy savings can be achieved for that process. But what we also see is that the ice making industry could probably leverage quite a bit on LNG coal, because actually ice is being sold for a very high price tag. And for what it concerns CO2 emissions reduction, the CO2 emission reduction, significant contribution CO2 emission reduction could come from the absorption chiller, which could allow to emissions by than 30%. Then there is some other scenarios that we wanted to assess. So for instance, we look at this alarm cycle, which has been demonstrated in the US from a company called Net Power. This is a supercritical CO2 cycle, which basically it starts with an air separation plant. It's an oxy-fuel combustion process where, you know, oxygen and gas is being mixed. There is a CO2 turbine to generate electricity. There is a stream of CO2 steam, steam that eventually the steam gets condensed, water is discharged, and then the CO2 stream gets pumped at higher pressure. Heat is being regenerated in the CO2 stream and goes back into the combustor, and a portion of this CO2 can be purged and directly captured for utilization. This is a pure CO2 stream. So this alarm cycle actually is a supercritical CO2 cycle with very high efficiency of about 60%. It comes with a large energy penalty due to the air separation, because this is, if you consider cryogenic air separation, this takes quite a bit of energy, and that is where, you know, we could leverage by using LNG coal to bring down the energy penalty due to air separation, and this could provide an additional 10% in terms of in terms of efficiency. And then, as we separate oxygen from nitrogen, some of this nitrogen, if liquefied, could be used for this new form of storage, which we call liquid air energy storage. So nitrogen as a byproduct could be liquefied and used for liquid air energy storage. So what is this liquid air energy storage? So liquid air energy storage is a process that liquefies and evaporates liquid air to store and regenerate electricity. So how it works? So of course you need power input, and basically we take air, ambient air, clean, compressed, refrigerated, and liquefied at minus 160 degrees Celsius in an unpressurized vessel. And basically this liquefaction process corresponds with the charging phase of this energy storage concept. Then the moment we need to basically discharge it, what we can do, we can pump this liquid air at high pressure, regasify the air, expand the gaseous air in a power turbine, then the exhaust will be basically air, gaseous air, and power will be generated. Now, during the compression process, the liquefaction process, there is heat being generated that can be stored and reused during the discharge phase. And during the regasification process of the liquid air, there is coal, which is being released, that can be stored and reused internally for the liquefaction process. So in this form, with this layout, the claim round trip efficiency is around 50%. Again, numbers vary. But if you could leverage on LNG coal as well as on a waste heat, external waste heat stream, then potentially you could achieve a round trip efficiency of more than 80%. And of course, I mean, this concept here is of interest because we can also consider a cogeneration operation for this facility in which we generate power as well as cooling during the discharge phase of the liquid air during the regasification process. Another option that we also can consider if you have natural gas is using high temperature fuel cells, in which we have a very high temperature heat streams that could be used to drive a supercritical CO2 cycle. So these are some of the integrations that could be considered that we put into our study to see what it could be the impact in terms of improvement, in terms of efficiency, as well as a contribution in terms of CO2 emissions reduction. So here basically are some of the different integration that we consider. Baseline is the CCGT with no waste heat or waste coal being recovered. Then we took the, I would say, the this configuration here with the CCGT plus absorption chiller with the air pre-cool before the CCGT and utilization of the coal for direct cooling. We could have chosen also some other application down here. And then we look at the integration of alarm cycle plus liquid air energy storage, because as I said earlier on, we can make use of the cold energy from regasification to assist the separation process of nitrogen and oxygen, as well as support the liquefaction of nitrogen that could work as a substitute of air, indeed, for the liquid air energy storage concept to serve as a storage system. And then solid oxide fuel cell combined with supercritical CO2 cycle, LNG core that could be used, for instance, with direct cooling. So again, if you look at the overall profit, so-called profit and the CO2 emissions reduction, again, you can see that as we go for different levels of integration, so if you move from this side to this side, you can see that the CO2 emissions reduction is, it improves as a consequence of the higher efficiency that can be achieved. But of course, I mean, one thing to consider is that as we move on this side, the TRL also decreases. So liquid air has been actually been demonstrated. This is fairly high TRL, but still not, you know, wide scale, large scale deployment. And for some of these, still in the papers that I can find some of these studies. So now, for what it concerns the R&D activities here, I put an NTU, but this is some ideas on some of the R&D activities that could be envisaged in the cold energy space. We see that there is a bit of a lack of research activity when it comes to thermal energy storage at the sub-zero temperature range. The numbers of materials available and papers and publication is improving due to the fact of having more and more LNG in the picture, and also maybe cryogenic hydrogen to be considered as a form of storage for the hydrogen. But we see that there is not so much as many as on the hot part. Also what we see that we still need quite a bit of work when it comes to look at system design and optimization and integration. So if you want to combine some material for thermal storage together with the heat exchangers, how to couple this together and optimize the design to meet a certain demand for what it and depending really what is the KPI for this. It is still not fixed methodology, and I think there is some work that could be done in this space. So the way we started it, indeed, we started to map which are the materials, the studies on and the experimental numerical studies, which are some of the applications, try to also capture some of the TRL for some of the works being done in each of these areas as we move lower in temperature. So I mean, not to go through each one of, not to go through each one of these, but basically there is still quite a bit of gaps, as you can see, as in this temperature range, and also the TRL seems to be pretty wide. But as I said earlier, there is not much work being done in each space. So there is an opportunity there to improve. And then for what it concerns the studies for the system design and optimization, we currently have set up this facility, which is basically, we call it a
So did we lose Alessandro now?
Yeah, cannot hear it.
Right. Okay, so maybe he's coming back, but he was coming back. And while we are waiting for Alessandro to come back line, maybe because we're moving quickly into the Q&A session for this session, there is a question to you, Professor Karimi, from Espen Jonsen. He says in your presentation you have calculated in your net present value calculation. You identified you simulated or identified the distance where net present value is no longer positive. So his question is, what about the distance? Is that a major driver?
Yeah. So I think just to answer that question very briefly, yes, definitely distance is a very, very major factor, because often the piping cost and the cost of transport, of pumping, and etc. outweighs your utility costs. Okay, so it depend. I mean, of course, the answer is not straightforward, right? There is no generic answer for any system, but the answer to your question will depend specific details of the system, because what you're talking about is distances of inter-node distances, and there are many of them, right? So I cannot really take one distance and say, okay, if I elongate it further or something like that, what will happen? But short, brief answer to your question is yes, it's a very major driver, and it can negate your solution. So beyond a certain distance, you may not be able to achieve what you want to do, because the capital costs associated with the piping could outweigh your costs in your operating costs.
Yeah.
I hope that answers the question.
Hello?
Yes.
Yeah, I'm back. Can you see
Yeah,
me?
you're back. Okay,
Can
so
I
just
complete?
continue, Alessandro. We'll come back to this question. I have a follow-up.
My apologies. I mean, the connection dropped for some reason.
Yeah.
But basically, this is just to say that we have this facility for design of a thermal energy storage system open to anybody who might want to use it. And also, we also been going to set up this cryopoly generation demonstrator, which is a 3.5 megawatt electric gas turbine with 10 megawatt absorption chiller. This is more like for testing purposes and also for research purposes. It's going to be H2 ready. And also we are going to test ways to store LNG underground, and we are going to set up again as a sort of living platform for what we call a cold innovation hub, where basically companies or researchers that may want to test and demonstrate technology leveraging on LNG coal can come and use it. So this is open across the research community and also to industry. So I mean, for what it concerns some of the work that we are doing, we are doing work on cold thermal energy storage system design, also looking at ways to store cryogenic energy storage, moving away from membrane technologies. And then to carry short release, we also want to see how we can recover make use of CO2 to enhance the cold energy to enhance CO2 capture. And also, yesterday has been announced by ENGIE that we, together with Surbana Jurong, we might work towards developing a 1 megawatt electric cryo cogenerator leveraging on liquid air energy storage system. So basically, in conclusion, these are very qualitative, but again, I mean, what I can say is that there is still a bit of question mark, and we need to achieve a bit of understanding, which is of some of the demand of cooling and refrigeration in Singapore. And again, this is knowing what happens in Singapore is not just it's not just useful for Singapore, because I said earlier on, might also serve as a pilot for neighboring countries. When it comes to waste heat and waste coal, I mean, this can offer quite a bit of an opportunity to quickly reduce CO2 emissions. Some of these options are readily available when we look at the cogeneration system that basically would help. But of course, that would mean that we will have to distribute energy generation island-wide. And then, of course, we also look at the different power cycles and thermal energy storage system that seems to be promising. And in terms of R&D, we think that there is still some work to be done in the cold and cryogenic energy space for what it concerns materials and energy systems design and integration.
Yeah.
Okay. Thank you so much.
Thank you very much, Alessandro, and also for being on time for this. I have a few questions. We have a few minutes for the next topic. Just one technical question to you, Karimi, and that is, I noticed in your WAHS, or the heat exchanger system solution, you added one heat exchanger. It was one more heat exchanger than the other solutions. Is that correct? That you can some of the solution is actually adding more equipment?
Yeah. So it is, sorry. It's possible, right, that adding more exchangers would allow you to be able to exchange more or say conserve more heat, so it's a trade-off between capital cost and the operating cost, and operating cost in terms of utility. So it is possible that by adding more exchangers, you could reduce the total analyzed cost.
Yeah, I have another question, and that is, I found your approach of this area-based optimization, where you actually have companies and factories are using a centralized heat exchanger system to optimize for a whole area. But wouldn't that, if you do this, you need to have a very close coordination of the operation of these different factories? So all of the companies have to coordinate how they will run their business. And in the worst case, if one business suddenly decides to shut down or increase activity, wouldn't that influence the entire operation of the others? Wouldn't you have a very complex agreements behind this one? What about liabilities? What about the responsibility for
exactly
for not delivering?
So those are all the hurdles that I remember. I had listed 8 or 10 of those issues, and so this is a very critical issue, right? It's interesting. I was presenting this talk at AICHE, and then Dr. Jeff Sorolla, who was at Eastman Kodak, he basically stood up and said, "Look, this is an interesting idea, but all issues remain." But I can tell you an example where actually we did this at Eastman Kodak, and so they had these two plants where they ran big pipes through between these two plants and were able to do heat exchange. So these are very critical questions. Okay, I think anytime you do integration, whether it is intra-plant or inter-plant, this question does come into picture, because you sacrifice some of your flexibility to gain some advantage. So there has to be not only economic agreement, but also some sort of operational flexibility. So we can think of a scenario where you were to add some equipment so that you can make the system robust. And so that's something which is also a topic of interest, but we haven't looked into that yet.
Okay. We do have another questions from Espen, and that is about the minimum cooling requirement. But I suggest something, and I know exactly where he's coming from. Espen is looking at opportunities for land-based salmon farming in Singapore, and he needs cold. So shall we come back to that when we have the discussions on the cold energy applications, which we will do a little bit later? And then maybe have Espen to explain a little bit about where he's coming from and what you need, Espen, to have your RAS system running. What kind of temperatures, what are the distances, what are the amount of gigawatts or gigawatt hours that you would need? So let's come back to that question after the next session. So with that, unless Espen, you feel that this is the wrong way, we just move on for the next area, which is on poly generation. And I see that your PhD student, Professor Gundersen, is here, Avinash Subramanian. So Avinash, I saw you tested your presentation. So please just show the presentation and start your lecture.
Great. Can you see the presentation?
We can see it. Yeah, we see it now on full screen, and we hear you very clear and sharp.
Perfect. Thank you. So hi, everyone. I'm Avinash Subramanian. And I'm a fourth-year PhD student at NTNU, and I'd like to present work on global optimization of energy-efficient poly generation systems, which is collaborative work with Professor Thomas Adams at McMaster University, Professor Truls Gundersen at NTNU as well, and Professor Paul Barton at MIT. So first, a brief background on poly generation processes. So poly generation involves the production of multiple products on the same location. And usually we also use multiple feedstocks. So we can have multiple products such as different fuels, chemicals, for instance, methanol, DME, olefins, ammonia, and so on, in the same plant location. So the motivation for poly generation is twofold. So first, we would like to exploit certain synergies. For instance, if we have two feedstocks, such as, say, natural gas and that feedstock, each would generate syngas of a different quality, which we could blend prior to downstream methanol synthesis to get the correct hydrogen to CO ratio for methanol. So for instance, natural gas would give a hydrogen lean syngas, and so, a lot of solid wastes, and coal would give hydrogen lean syngas, and natural gas would give hydrogen rich syngas. And we can blend these two to get a correct ratio for methanol. In addition, heat integration, say between endothermic natural gas reforming reactor and an exothermic solid waste gasification is also another opportunity for increased energy efficiency. The second motivation for implementing poly generation is that we can implement a flexible design which increases competitiveness under uncertainty. So flexible design means we oversize equipment such that we get operational flexibility and can so adjust operating conditions in order to maximize the production of the most valuable product mix. And so this allows for exploitation of price peaks and higher profitability under uncertain price conditions. So the trade-offs we're optimizing are the increased capex for larger equipment because of oversizing, and the versus the increase in annual operating profits due to operating flexibility. So this flexible design problem can be formulated as a stochastic program where you have decision variables for the capacity as here and now variables, which are fixed between the realization of uncertainty, and decision variables for the operating conditions as wait and see variables, which you adjust after realization of uncertainty. This slide explains why we used a hybrid of a waste tire and natural gas feedstock. So first of all, there are plenty of waste tires in the world, and conversion through the syngas route gives us a useful waste disposal strategy in contrast to stockpiling. In addition, waste tire is also fairly homogeneous and has a high energy density, which is comparable to coal, and also has a high volatile matter content. So, and lastly, if we were to combine waste tire and natural gas, the syngas ratios work out. So, as I mentioned, waste tire gives us hydrogen lean syngas, natural gas gives us hydrogen rich syngas, and we can blend, say, to get correct ratio for methanol. So we eliminate the expensive water gas shift, upgrading syngas downgrading steps. So this slide presents a superstructure of the poly generation system this slide presents a superstructure of the poly generation system we studied. So we have waste tire, which is mixed with water, and oxygen from an ASU goes through a gasifier and is cleaned up, and then we get syngas. We also implement a water gas shift just to test things. Then with the natural gas, we use the autothermal reforming approach, and we get hydrogen-rich syngas, which you can blend. And we consider three products: synthetic natural gas, methanol, and further on DME and methanol to olefins, or direct production of electricity through a gas turbine. We go further to produce liquefied synthetic natural gas. So this optimal flexible design problem can be formulated as what's termed a scenario-based two-stage stochastic non-convex MINLP. So here the Y, as I mentioned previously, are the here and now first stage variables for equipment capacity. And the objective is a function of these first stage variables and the second stage operational decision variables, where H indexes the scenario of uncertainty that is realized. And we also have constraints on the first and second stage variables. So more precisely, for the flexible poly generation system, the objective is to maximize the expected net present value. So we have the capital costs, which are a function of the first equipment capacities, Y, and we have the annual operating profits, which are for each scenario, which is a function of the operating decision variables X, H. And the first stage constraints are the capital cost model. Second stage constraints are the mass and energy balance operating cost and annual net profit model and scale constraints. And we also have these complicating linking constraints, which make things more difficult between the first stage and second stage variables. So throughput should be less than equipment capacity. This slide presents implementation details, which I won't spend much time on. So we basically implement mass and energy balancers in Aspen, generate surrogate models with Alamo, and formulate the non-convex MINLP. Great. This slide presents the uncertain parameters, which basically are the product prices of natural gas, electricity, methanol, DME, ethylene, and so on. So we got these. We assumed the prices belong to a normal distribution, and we got mean and standard deviation values from historical prices as presented in this table. So we formulate the optimization problem using a recently developed software called Gossip, which was developed 2018 at the Paul Barton's lab at MIT. And I won't present details here, but I will only say that Gossip provides a versatile C++ framework for modeling these two-stage stochastic programs. And also, we have an efficient decomposition algorithm to solve for a large number of scenarios. So it makes solving such problems easy and efficient. So next, we present the results of the optimal flexible design problem. So we had two case studies. So one case study in which I had two scenarios of each of the 5 uncertain parameters, and so case study 1, so 32 scenarios in total, and case study 2 with 3 scenarios of electricity and natural gas and 2 for the rest, so 72 scenarios in total. We also compared with the deterministic case where all uncertain parameters are assumed to take on their mean value, and this is termed the mean value problem. So it's just one scenario. We see that the capital costs are substantially higher for the flexible designs of case 1 and case 2. So this is not a flexible design, but here when we take uncertainty into account in case 1 and case 2, we get a flexible design. So this is because we are paying for the higher capacity, and we're paying to get the higher operational flexibility. Okay, so moving on to the operational modes and economic performance. So for the mean value problem, we just found that we get a case in which natural gas is converted to electricity, fairly basic. But the thing is, this is only true if all prices remain exactly at the mean value problem, which is not feasible. So if we're to take uncertainty into account, we see that the operating mode shifts to favor multiple other products at their price peak. So for instance, if DME and electricity experience higher prices, we shift the operating conditions to produce that, and we produce methanol when methanol prices are high, electricity when electricity prices are high, say day-night variation and so on. And so the main result of this work is that we get a substantial increase in NPV if we take this uncertainty and variation in prices into account and build a flexible design. So this the expected increase in NPV is in the range of 35 to 55%. So $884 million versus $560 million. This is for a 900 megawatt plant.
Three more minutes, Avinash, please.
Great, thanks. There are also some technical measures we can use to quantify the benefit of implementing a flexible design. So this termed value of stochastic solution, which increases as we consider uncertainty. I'll get into that if there's interest. So this slide talks a bit about the computational performance, which is important for solving the optimization problem, especially if we're to include many scenarios. So we see that solving the two-stage stochastic problem quickly becomes intractable if we're to use the state-of-the-art, which is Antigone. So we really can't go more than 16 scenarios. Yet using a decomposition algorithm gives us favorable scaling to up to to many scenarios. So in conclusion, we see that implementing a poly generation system gives improved energy efficiency, and this is partly because, as I mentioned, for these two reasons, we get heat integration of the ATR, which is autothermal reformer, which is endothermic, and tire gasifier, which is exothermic, and blending of hydrogen-rich and hydrogen-lean syngas streams. But the major result of this work is that implementing a flexible design gives a substantial increase in expected net present value. And we also show that using the decomposition algorithms that were built allows us to take uncertainty into consideration with more scenarios. So thanks a lot.
I'm sorry, I was muting. I was saying that thank you very much, Avinash. And I also said that we will wait with the questions until the second speaker, Professor Chua, Ernest Chua from NUS, is giving his presentation, and then we take the questions for both of you after that.
Can you see my screen?
We can do, and could you increase your voice a little bit, I think? We hear you very weakly. But we see your screen.
Can you hear me now? Better?
Yeah,
Is it better?
we can hear you.
Okay, great. Right. Let me go to the first slide. Okay. Can I start?
Yes, thank you very much, Professor Chu. I just want to say that you're from NUS, from the Department of Mechanical Engineering. So please go ahead.
Okay. Good afternoon to everyone. My name is Ernest. I'm from the Department of Mechanical Engineering, NUS. So today I'm very privileged to be here to share with you a project that we've done for the last 4 to 5 years. Okay, this project is basically entitled 4-in-1 Smart Utility Plant, which is specifically designed and engineered for the tropical climates. So in short, right, we are looking at connecting the water energy nexus. That means we hope to produce electricity, air conditioning effects, hot water, and portable drinking system all in one compact unit. So I see the previous speaker has done a lot on coal energy and so on. So I'm doing on the reverse side, right? I'm doing on the hot side. So I'm looking at the utilization of hot energy to produce useful utilities. So basically, this is a system that we have designed in the lab. The schematic is presented here. So what we have is we have the injection of the natural gas, right, to a micro turbine system. The micro turbine system will deliver the electricity, as we know. And then as a turbine delivers the electricity, it also has the waste product, which is the fuel gas. The fuel gas of the micro turbine is about 250 to 300 degrees C. So that is actually very good heat for us to do a lot of useful work. So we utilize that fuel gas, and then we go through a boiler. We can produce the steam, right, of different temperature and different pressure. And then the remaining of the fuel gas, we can tap it out. We go through a heat exchanger, and we tap out the fuel gas to produce hot water at 90 degrees. So this hot water at 90 degrees, basically the first injection of the system, we go through a 2-stage absorption chiller. So when you inject it at 90 to 100 degrees to absorption chiller, it produces a chill water effect, right? So chill water is being produced at this absorption chiller. And the outlet of the absorption chiller comes out is about 70 degrees, 70 to 75 degrees, and that is still good heat, right? The good heat we inject to a absorption chiller. So this absorption chiller, no doubt, is smaller capacity than an absorption chiller. It produces chill water at a lower capacity, but one of the key advantages of using the AD chiller as opposed to the AB chiller on the secondary side is that it also helps us to produce potable drinking water. So any feed water or seawater that you inject into the AD chiller, right, it comes out as potable water besides producing additional chill water, right? So the injection is at, again, about 70 to 75 degrees. The outlet of the absorption chiller is about 45, maybe about 50 degrees. So that heat is still good heat, right? Normally, if you reject that heat will be higher than the ambient temperature, and that heat will cause some microclimate effect if you directly reject that heat. So what we do is we utilize that heat and use it for regeneration of next generation of what we call the absorbent. The absorbents are these super absorbents which help to dehumidify the air. We know that in tropical country, one of the major energy guzzler is air conditioners, right? They consume a lot of electricity, primarily because of the fact that our humidity is very humid, right? The energy used has to dehumidify the air, remove the moisture before it can do the sensible cooling part. So so when the air goes through, the super absorbent also absorbs the moisture, it has to push out the moisture again, right? And then we use this regenerated heat at about 50 degrees to regenerate. So after the regeneration of this super absorbents, what we get is a very dry air. The air is dry, right? The air is dry, and then the reject of the heat is about close to about 35 to 40, which is very close to Singapore ambient temperature. And then if you release that heat to the environment, it's actually more acceptable to the environment without causing microclimate effect. So in other words, if you utilize this system here, we are looking at expecting energy reduction about 25 to 30%. And then this whole system can be compact into one single mini plant. And this mini plant can produce 4 useful utility: electricity, steam or hot water, right? You can produce air conditioning effect to the, even the dry air, and then you can also produce the potable drinking water. So this is a schematic, and this is the real plant that we have developed in the lab. You can see the micro turbine. The micro turbine in the lab is about 55 kilowatt per unit. We have 2 units of this, so we're giving us about 110 kilowatt of electricity. And the boiler is here, right? We produce boiler, hot water or steam. The reject heat from the boiler will go through the 2-stage absorption chiller. The reject of the will go to the AD chiller, right? This is a 4-bed AD chiller where we can produce additional chill water. At the same time, we can clean up your brackish water, your desalinate the water and produce potable drinking water. And the additional heat coming out from the AD chiller is about 40 to 45 or 50. We can use it to regenerate the super absorbent, the desiccant, to dry the air. Alternatively, we also have a second stage membrane dehumidifier to even further dry the air. Here, for some special applications, some industry, they need the air to be particularly dry, right? Normal in air conditioning, we need the air to be about 12 grams to 13 grams of moisture. For certain industry like the wafer fab, they need the air to be about 4 to 5 grams. So using this two, combine the absorption chiller and the membrane, we can get about 4 to 5 grams of moisture, which we can produce with dry air. And then additionally, recently we have coupled to this system a dew point evaporator cooler. This is one of our key inventions where we can get produce the air condition of the air, where this evaporator cooler does the sensible cooling. So you get cold and dry air simultaneously, right? Combining with this entire system. So this is a mini plant that has been running in my lab for quite some time. We'll be collecting a lot of impactful results, and we have been sharing to the community, to the journal publication, and so on. So if you look, if you compare to conventional system, the turbine is the same. There's nothing different about the turbine, whether is it a conventional or the quad gen system that we have developed. But in terms of the hot water, we are harvesting the waste heat. So the hot water is basically free energy, right? Because that is used from the fuel gas from the turbine. And then the air conditioning system, we are using absorption chiller all running on waste heat. So the energy consumption to produce the air conditioning effect is actually much reduced. And we are looking at conventional system, conventional plants are 0.7 to 0.8 kilowatt per ton. We can shave it to about 0.3 to 0.4 kilowatt per ton. The potable water, if you use reverse osmosis, this is the amount of energy people are looking at for RO system, 3.5 kilowatt hour per meter cube. This is free energy because as the absorption chiller AD chiller produce the chill water, it produces a potable water simultaneously, right? So that is a byproduct of it. So that is basically free potable water you are getting. So if you do some of the back of the envelope calculation, you are looking at about ensured 25 to at least 30% energy reduction compared to the conventional.
Did we lose Ernest as well?
Looks like.
Oh. Okay. It's a bit unstable, the whole. So we give him a few.
He's still there. I can see his name appearing in the list.
Yeah. All right. We give him a minute or two.
Volume, which is about 5,000 meter cube per hour, And
Professor,
the amount
Professor
of water,
Professor Chu, I think we lost you for about 1 minute. So if you go one slide back, I think.
Okay.
Yeah, you were talking about this one, and I think the last thing you said it was the percentage energy reduction.
Okay, so if you look at this, the overall utility production using this innovative quad gen system versus the conventional way, meaning that each of these utility is produced individually, right? You are looking at about 25 to 30% energy reduction guaranteed, right? And then if you size up the system to about 10 megawatts, right, we are looking at CO2 reduction about 2,500 to 3,008 metric tons per year. And this is equivalent to about 200,000 to 300,000 cars per year. That means you remove this number of cars from the road, that is the equivalent amount of CO2 that you shave it using this system versus the conventional system. So the innovation in this combined plant, right, we have developed is, you can see it's like a Lego system, right? We have innovative systems that are being pieced together to form up this entire quad gen system. So one of the key technology that we developed is the membrane system to remove the moisture from the air. This membrane can remove up to up to 5,000 cmh of air, and with that airflow, you are looking at about 2 kg of moisture being removed from the air per hour. And then we have the super absorbents that we can coat on any metallic solid surface and start to make heat exchanger become latent system as well. Besides removing the heat exchanger also remove the moisture at the same time. And the beauty of this new material that we discovered is that it only regenerate about 40 to 45 degrees. If you use silica gel or Zolite's commercial material, you are looking at regeneration about 80 to 120 degrees C. So those kind of high temperature regeneration is something that it doesn't make sense, right? You need something that is a much lower heat to regenerate. So the two-stage absorption chiller is also designed in-house. We have a two-stage system where we use a new kind of hybrid coolant refrigerant, which is the ionic water and water. Conventional absorption chiller, they use lithium bromide and water. Has a lot of problem. It crystallizes for this kind of humid climates, right? Crystallize, you see, it crystallizes, your absorption chiller has a lot of problems, right? So this combination of the new kind of coolant refrigerant helps to minimize. I should say that the chances of crystallization is practically very, very minimal, right? Compared to lithium bromide and water. And this combination of material is less corrosive. Most importantly, it allows us to double stage the absorption cooling process. And then we can realize about 15% more energy efficiency. That means you can produce about 50% using the waste heat that is injected to this two-stage system. You can produce about 50% more of the cooling effect from the absorption chiller. The other key innovation is the 4-bed 2 evaporator absorption AD systems, which I mentioned. These two AD systems, because it's heat driven, right? So electrically, you can realize very high COP, about 20 to 28, right? Conventional vapor compression system is only about 4 to 6. This is about 20 to 28. Big breakthrough, right? And then this 4-bed system, we only need about 65 to 70 degrees of hot water input to produce the chilled water. And it produces chilled water at two different temperatures, about 7 to 12, and then 15 to 20. Okay, this is the typical temperature of the chilled water that's being injected to most of the AHU to remove the moisture and also to cool the air, to supply the cold and dry air to the building. Whereas 15 to 20 degrees is very appropriate for what we call radiant cooling, right? A lot of places, they look at sensible removal using radiant cooling. So this chilled water at 15 to 20 is very appropriate for that kind of radiant cooling effect. And then most importantly is as it produces chilled water, it produces your potable water. Any brackish water, seawater, water that wastewater you can inject in, it comes out clean potable water that you can get. And this system we have designed in the lab is about 30 kilowatt capacity. So this is the pictorial version of the system that you can see there are 4 beds, right? 2 beds to produce 2 different chilled water at 2 different temperatures. And as it produces chilled water, the clean water is being produced at the same time.
3 minutes more, please.
Yeah. And then you ask how good is the clean water, right? The water is very good, right? If you look at the product water, it's about 28 microsiemens compared to your mineral water. So I'll not go through this, you have seen it. And one of the technology that we have is the dew point evaporator cooler. This dew point evaporator cooler is unlike your swamp cooler, right? This system the air doesn't contact with the water, but at the same time, it uses the latent heat capacity of the water, the HFG, to actually remove so much of the heat from the water that you can actually produce the cold air. And we compare with some commercial product. This is one of the best cooler in the market using water-based. We are about 25 to 30% big improvement compared to them. And you ask the idea, if you use the membrane on a super absorbent to remove the moisture, what is the impact on a cooling system? The impact is that your chill water that typically you supply to your AHU, right, from your chiller, supply to your AHU, normally is running at about 5 to 7 degrees. If you have a system that decouple the sensible and latent, you no longer, your chill water no need to run at 5 to 7. It can run at about 13 to 15. And every degree increase in the chill water, your cooling plant is looking at about 4% increase in efficiency. Right? These are real data from the lab. And one of the big market here in Singapore is district cooling. We are looking at how district cooling impacts the whole cluster of buildings in terms of saving energy for providing air conditioning effect. If, for example, look at from a big picture, if all the AHU have the membrane or the super absorbent to remove the moisture, right, then your district cooling plant doesn't have to supply chill water at 5 to 7 degrees. Your chill water can be supplied at 13 to 15 degrees, right? And then that not only see big energy efficiency in terms of 4 degrees improve in efficiency for every degree increase in your chill water temperature, but also the chill water running at higher temperature, right, which is the pipes are all buried underground, they loses less heat because now they are running at higher temperature, there's less heat loss. And then that is a big impact, right? You save more energy, both from the plant perspective as well the heat losses through the piping. And we are looking at Singapore in future, whether the whole Singapore can be district cool, right? That means the Singapore government can sell you district the chill water, right? Instead of you have individual split unit aircon in your house, right? If the government sell you chill water using this concept and run it, the whole Singapore is one big district cooling plant, right? Then that will save a lot of energy and a lot of reduction in carbon emission. So what is the impact of this 4-in-1 utility plant? We can apply it to underground these cities, right? District cooling plant. We can also apply it to floating platform, right? Floating cities and so on. Because all these cities, we need water, electricity, hot water or steam. We also need potable drinking water. Okay, now we have digitized our systems and make it very portable.
One more minute, please.
Okay, sure. Okay, so we can control this our plant that we designed using our handphone. If we want to produce more chill water for the day, or we want to produce more potable drinking water, we can just control it using the handphone anywhere and in any part of the world. And we can also use that to do diagnostic whether any part of the plant has any faulty problems, right? We can eradicate. So here the combination of this quad gen system will allow us to combine the 3 grid together, right? Meaning the water grid as well as the electricity grid. Right? We can actually optimize this network, 3 network together into one, right? Electricity, potable drinking water, as well as the thermal grid, which is the chill water for producing cooling effects to your building. So in conclusion, we have this designed a quad gen system. We have tested, we have shown the numbers and shown the improvement in the efficiency. So for output, chill water, hot water, steam, potable water, and electricity, we have decoupled the sensible and latent cooling for such a plant. That means the chill water can be provided at higher temperature to see better improvement in the kilowatt per ton for the cooling plant. Novel technology we have produced, the double stage absorption chiller, advanced the 4-bit driven AD chilling system, membrane, super absorbent dehumidifiers. And now the beauty of this is that this whole entire plant can be controlled and optimized, anywhere in any part of the world. And this is very appropriate for smart city application, right? You want to control your plant, see how your plant performs, and control the individual utilities provision on a day-to-day basis. So with that, I think I will end my presentation here.
Thank you very much, Professor Chua. Anyone that has a question, we are a manageable number of attendees here, so you can raise your hand and you can ask the question by taking the microphone as well, if you like. We have a few minutes for discussion and questions for this, but let me just start with a reflection from myself to Dr. Avinash. I think your application in your case, it was secondhand tires, which is a dense polymer, if you can put it this way. I assume your application can be used for any kind of polymers based. And I'm thinking in Singapore there is this dual problem of waste management which basically now, as far as I understand, most of the waste goes to incineration, producing heat, of course, steam, and then it's deposited at some of the islands. At the same time, there's a very advanced polymer and petroleum-based industry, chemical industry at Jurong. So maybe I should ask the questions to our Singaporean colleagues here. To what extent would Dr. Avinash's concept be applicable for Singapore, for better utilization of and recycling of polymers, perhaps, or better utilization than just the conventional incineration? So I'm not sure exactly who I'm asking this one, but maybe to Professor Karimi or even to Professor Chua. How is this done in Singapore right now?
Well, I'm not aware of something being done at this point in time. The only, I mean, this sort of conversion, I mean, we talk about plastic recycling and all that, but I don't know how much of that is being done in Singapore right now. I have heard that there is some effort in India, for example, to recycle plastics. But no, I'm not aware of any. Maybe some other persons have knowledge.
Yeah, Professor Linga or Professor Chua, do you know how?
Sorry, I'm not very familiar with this incineration process.
I could briefly mention of this startup company in the US termed Sierra Energy, which is looking to do a waste to energy conversion for the US Army. So the US Army has the highest energy costs in the world, and they also have a lot of waste in their bases overseas in Afghanistan and so on. So this is a company that is building gasification-based processes for converting tire, municipal solid waste, plastics, and so on. Basically for army bases around the world. So that's a nice start for this technology.
Yeah. But your concept is still to make syngas out of polymers, and you mix the different syngases to the let's call it the optimal carbon versus hydrogen constitution, I guess. And then it will be incinerated, or it will be burned and converted into energy and heat and electricity, I assume. So it's not so much of reusing the polymers, but it's more on a much better way of burning or converting waste into energy. Isn't that correct?
Yeah, but we also look at production of DME and ethylene and propylene.
Okay. Yes. Yeah.
Thanks.
But it's interesting. We are working a bit with the National Energy Agency, environmental agency here in Singapore, to look at better ways of recycling and even reverse vending. There will be a tender out now quite quick to implement or return of bottles and PET bottles and stuff like that. So definitely there are huge opportunities in this space, I believe.
I have one question for Prof. Chua. Ernest, thank you very much for your nice talk. As system gets more and more complicated, how do you calculate an overall efficiency of the system? So we have a system in which all kinds of energies are involved, right? So for your systems, how do you convince somebody that you have a more efficient system? I mean, apart from the fact that yes, you are trying to extract every pinch of energy from every place, is there a quantitative measure?
Usually when we do that, right, we let the energy flow from one component to another component in the system. We will compute the input and the output. I think that is something that everybody is very familiar with. So the losses is the key, right? The losses, whether through entropy generation or exergy losses and all this. So this has to be accounted, because this cannot be recovered and cannot be put into useful effect. And then so from most of the time when my team or my group look at the conversion side, we would like to plot everything we call, I think I will be very familiar, the Sankey diagram, right? So from the Sankey diagram, you can see the energy conversion from one stage to another stage, and then also can look at how much losses is being losses being made through all the different parts, right? Whether it's due to heat losses, whether it's due to friction effects, or and so on, right? So that is how we look at it from one component to another component. We draw a stage, every stage we draw a Skanky diagram, and then we integrate the whole diagram together, and then we do our calculation from there, and then look at how it flows, the energy flows. So the injection of the energy versus the useful effect, right, will give us the overall efficiency, because there will be losses coming out. So to optimize it means you try to minimize the losses, so that the injection of the original fuel resource going in will be converted as much of it to the useful effect, and very much of it is lost. So sometimes we do a second law entropy optimization. That means we try to minimize through certain things, better insulation, trying to maintain your equipment, right? Don't let your equipment, the performance depreciate so much, right? And then we can see that there's some impact. It's not, sometimes it can be up to about 3-4% improvement just by doing simple things, right? Better insulation and so on.
Thanks.
Yeah.
Thank you very much to Karimi and to Professor Chua. I think we have to move on to the next theme, which is further into cold energy. Alessandro was looking or touching into it, or more than touching into it, and actually going into it. But we'll go even further, Professor Linga, into utilization of LNG. So if you can take the floor, please, and give your presentation introduction to this theme.
Thank you, Per. I would need your help to run the slides.
All right. Okay.
I apologize for that. There is some system error. I'm unable to share through my iMac. Maybe next time when we meet, I owe you a coffee or a beer for that. Okay.
I'll take the latter, obviously. Let me just see if I can then share my screen, and let me see. Just do like this.
Usually I carry my laptop. Today I didn't carry it, so I have to rely on you. Yeah. So looking at the program, before I start my presentation, I would like to extend my gratitude and thanks to Per for putting together this excellent program, along with the session chair. That includes my colleague and someone who I work closely with, Prof. Karimi and Professor Truls Gundersen. So today I'm going to focus my talk on LNG cold energy utilization.
Oh, did we lose him?
I think we lost him.
No, I can see him now, but the voice.
But we can see, but we cannot hear. Praveen, we cannot hear you.
The sound. You're muted, Professor Linga. Somehow you muted yourself. Oh, there we go.
Okay. Sorry, guys. Yeah. So we had an excellent talk from Alessandro, giving us the complete overview of what one could do with LNG cold energy utilization. So kind of mine is a logical extension of that. I'm actually the Vice Dean for Communication and Outreach at FOE, recently got. And I'm also the Dean's Chair Associate Professor in the Department of Chemical and Biomolecular Engineering. I did a brief introduction about myself to the audience here. I did my bachelor's degree and master's degree in India, and then I went on to pursue my PhD in University of British Columbia. From there, I joined NUS as an assistant professor in 2010. So this completes a decade of my time in Singapore. I mainly work on gas hydrates and environmental sustainability and clean energy applications. Under clean energy, we have a huge activity going on the gas storage side. I'm also working on methane hydrates as an energy resource, how to tap into it, develop technologies and methods to efficiently produce energy from methane hydrates. We also focus on data center cooling. This is where some of my talk is going to tailor towards. We work very closely with Keppel data centers on that. Can you go to the next slide, please, Per?
Yep.
So if you look at the global demand for natural gas, I think Alessandro did touch a little bit about that. One key important takeaway from this World Energy Outlook 2019 data is that natural gas is expected to grow the highest, right? 43% increase from its base level 2019 to 2040. In fact, if you look at renewables, it comes second, around 37%. And whereas coal is likely to see a decline, as you would see there, a 10%, minus 10% for that. So this means there is a strong forecast for natural gas, and IEA actually has already proclaimed this century to be the golden era for natural gas. No matter people talk about hydrogen, hydrogen will never become a important transition unless you produce hydrogen from renewable sources or from water. So that sort of a challenge still remains, but what is in front of us is that over the several decades, we would likely see a transition into a gas economy dominated by natural gas, perhaps, and transitioning into hydrogen, hopefully in the future. On the right-hand side, if you look at the LNG supply-demand gap, it is expected, the forecast is that there's going to be a huge demand for LNG because as and when natural gas markets expand, the dependence on natural gas expand, LNG is going to be the likely mode of transport of natural gas from producing countries to energy receiving or energy hungry countries like South Korea, India, Japan, and so on. So there is a positive outlook for both natural gas as well as LNG. So this brings me to my next slide, please. Yeah, so this brings us to what is the importance of LNG in the context of Singapore. If you look at the global numbers here, I just highlighted, the orange ones are the exporting countries. You can see there Norway is exporting roughly around 4.7 MTPA per annum. And if you look at energy, United States, it's huge. Australia, I did not, my team didn't put a number for Qatar. Qatar is also exporting a lot of natural gas. So, but if you look at the greener numbers, the energy importing countries or natural LNG importing countries, Japan imports a lot of LNG, 210 MTPA. If you look at Singapore, we are very small, still big, I would say. 11 MTPA is what the target is for Singapore. India is expected to import more of natural gas. Recently, they have signed huge 20-year deals with the United States energy companies. So the projection here is the main transport of natural gas is LNG. So what happens is that LNG comes in the mode of ships to Singapore. If you actually look at the numbers I've listed in the slide, as we speak now, 95% of the electricity in Singapore is actually generated by natural gas. Of this, a few years ago, as per the stats of a few years ago, LNG contributes to about 30%, 25 to 30% of the overall energy requirements. Right. So with that in mind, this tells you that there is a large volume of LNG that is coming into the nation in the form of ships. Can you please go to the next slide, please? So then what happens once LNG comes in? I know the next speaker is that we have lined up is a fantastic industry speaker, Raj. He's going to talk a little bit more about the concepts that's going on in the LNG terminal and the processes that's going on. But I would like to just give a brief overview. Once LNG comes into the island, it gets into these tanks. And what you see on the right-hand side is a LNG tank. Then this LNG cannot be kept in the tank for more than 1 week because of the continuous boil off and other boil off managements that would be required in order to minimize that or keep that under control. So what then naturally happens is LNG is then gasified, or what you say is regasified, by removing the cold energy. As Alessandro highlighted, LNG comes in at minus 160 degrees Celsius. So it has to be converted back or it has to be increased to 20 degrees Celsius in order to supply natural gas to the power grid or the power pipelines, we call them, which then gets transported as a gas for power generation. This is what typically happens in the SLNG terminal in Singapore and perhaps worldwide as well. So if you look at per ton of LNG, or if you look at the cold energy available in per kg basis, there is about 830 kilojoules of cold energy per kilogram of LNG that is available for harvesting or utilization. As highlighted by Alessandro, right now it is not being harvested or utilized. Rather, it is just a simple heat exchange using seawater as a heating fluid. There is a heat exchange and the power grid. Can you go to the next slide, please? So if you look at what we could do, actually, Alessandro's slide had many more options up there. I have taken down some of them because for me, I think if you look at Singapore, there are three important factors when LNG cold economy comes into play. Number one is reliability, very important factor given the SLNG's mandate and the requirements are. The second one is speed, and the third one is scale, because per hour we are processing in the terminal nearly 200 tons of LNG on an hourly basis. So speed, scale, and reliability comes critical. So I've actually listed some of the concepts that we could use in Singapore for LNG cold energy utilization. But as Alessandro highlighted, there are many things you could do. Okay, so if you look at the left-hand side, you could actually generate power. This is where Raj is going to come in and maybe talk about some practically relevant ideas on that. So Osaka Gas in Japan has been doing a lot of R&D work with regards to cryogenic power generation for nearly 30 years. Okay, so I leave it with that there. It's a very mature technology to use organic Rankine cycles to generate power. The second option, also touched by Alessandro, is you could use it for cryogenic air separation. Cryogenic air separation requires extremely low temperatures. So you have to look at how efficiently the cold can be transported with speed and scale in mind if you're looking at trying to do cryogenic air separation. The third crazy idea, which was also touched up by Alessandro, and I also feel that you could use it for cryogenic CO2 capture. Cryogenic CO2 capture is possible, but then there are several challenges involved as well. In Singapore, the CO2 concentration in the exhaust stream is very low, typically around 5%. So that may give additional challenges if you are looking at cryogenic-based carbon CO2 capture. Now, on the right-hand side are applications that I would want to focus a little bit more here. One is water desalination. We could use LNG cold energy to desalinate seawater. And we could also use the cold energy to use it for data center and district cooling. My colleague and good friend Ernest Chua presented a few slides about the overall expectations of what we think is the future is to look at Singapore Island as a whole unit under under district cooling system. So there presents lots of opportunities in looking at if we could integrate the cold cycle loop into the overall plans of district cooling, centralized or distributed district cooling systems. The fourth one is as also on the right hand side. The last one is the cold energy storage and transport. Alessandro touched a little bit about that as well. So I'm going to show you some ideas of what we plan to do in my lab. I'm an experimentalist. Perhaps we do things that would work and we do make them work in my lab. So next slide, please. So if you look at the first part of the right-hand slide that I had, it actually showed you water desalination. You could actually use freeze desalination as a method. Freeze desalination is simply ice formation. You need -10, -15 degrees to form ice with seawater, and then you can separate. That's not a new idea. It's been there for 78 years. But what I work with here in Singapore is we look at hydrates as a technology enabler for seawater desalination. The concept is simple. If I take seawater and I mix with suitable gas that actually forms hydrate, hydrates look like ice. What you see in the slide here is a ice-like chunky mass, but that's actually above the freezing point of water. You can actually form hydrates above the freezing point of water. So when you mix a suitable hydrate former with seawater under colder temperatures and moderate pressures, you can form these white mass crystals. And if you separate the mass crystals, as I've shown in the schematic, and if you warm them up, it's just like melting ice, right? So you could just apply a little bit of waste heat to dissociate hydrates. You would get water and the gas out. So if you look at the water, that water is the purest form you could expect theoretically, right? Because salts do not form hydrates. So salt ions get occluded when you subject seawater to hydrate formation. Now, if you look at some of the highlights, this particular technology requires cold energy in order to form hydrates, not below the freezing point, but slightly above the freezing point. So that is an avenue for us to utilize LNG cold energy. Salts get rejected automatically, as I said. There is no chemical reaction here. This is just a weak van der Waals forces interaction, like ice formation. So that means you don't need significant energy to break down and recover the water if you form hydrates. We can treat high TDS. We have done experiments treating salt concentrations up to 7 to 8% in my prototype. So we can actually extract more water out of the high brine solutions, which is what we would explore in the near future. And we have developed a prototype which is patented. Given the type of audience, I've not prepared slides to go into the detailed aspects of it. Please feel free to contact me. I would be happy to share details later. Now, if you look at the overall energy analysis of coupling a seawater desalination plant with LNG cold energy, in collaboration with Prof. Karimi, we did a simulation paper which we published in Applied Energy a couple of years ago. We did the overall processing integration, mainly focusing on energy integration and heat integration. We have come out and published data whereby if you couple a seawater desalination unit using hydrates into an LNG cold energy system, you could produce potable water at 0.84 kilowatt hour per meter cube of potable water, as Prof. Ernest Chua highlighted in the previous talk. Roughly, reverse osmosis gets you the energy consumption for a reverse osmosis plant is around 2.5 to 3.5 kilowatt hour per meter cube of water. So there is a potential to develop a technology that can actually utilize and produce water. Why water? Because water has a high cost. We have done the cost analysis as well. We have published it last year in DSAT. The cost of water produced using this coupled technology is around $1 Singapore per meter cube of produced water. So next slide, please. So then the second idea that we have recently started, last year we got funded by
another
IMDA.
3 minutes,
yes,
please.
We got funded by IMDA, supported by the actual money comes from NRF, but the agency that administered is IMDA. I'm not going to talk into the details of it because of the IP involved and sensitivity of the data we have generated. So if you look at the overall scheme of this, we want to use LNG cold energy. And we want to use hydrate as again, another form of hydrates as a medium to strip the cold energy. And with that cold energy, we want to run a data center unit. So basically, we want to eliminate the use of chilled water, replace chilled water by using a semiclatrate as a fluid medium. Now, there are several advantages here. You could actually utilize LNG cold energy from a terminal. Again, here speed and scale comes into play. We have demonstrated that we could achieve about 20% improvement in the overall energy efficiency. And data slurry, use of hydrate slurry actually reduces the size of the cooling requirements in a data center. That essentially means more space to store data and make more revenue. Next slide, please. So this is what we use as a cooling medium. We use water-based fluid. Again, this is a classical form of hydrate formation. We call them semiclatrates here because 95% of the component in the fluid is water. Only 5% is the hydrate former. In this case, you don't need any gas. We just use a liquid former. For example, here I've shown you a semiclatrate structure. If you have a water solution, and if you, as you see in the left-hand side of the slide, and if you mix it up, you can form what you see, a white mass. And this is a slurry form. Up to 48%, you could have it in slurry form. Can you run that video? We can actually form these hydrates extremely fast in the laboratory. I'm giving you an example. This is a hydrate slurry formed. As you can see, within 7-8 seconds, you can nucleate and form these hydrates. And as what you see there is a close to 35-8% system that is perfectly well mixed. And you know, one of my collaborators in Shanghai Jiaotong has shown 1,000 cycles of recyclability. So it's a perfect material that can be used. Please go to the next slide, please. So this is the overall research roadmap we have with Keppel Data Centers and SLNG as our partner. We are actually in the current phase of screening semiclatrate materials. We are also in the process of designing our prototype. We actually plan to develop a combined prototype that can actually serve as a model for utilizing cold energy to cool data centers. Next slide, please.
Prof. Linga, we're running out of time. Could you please come to your conclusion?
I'm closing down in 1 minute, yes.
Oh, okay.
I mean, less than 1 minute. So if you look at this slide here, this is again a high-level slide touching upon something that Prof. Chua, Ernest Chua touched as well. We want to look at using this medium as a replacement for the need for ice storage system in an overall centralized district cooling system. We can carry more cold. The earlier slide actually highlighted the numbers. So this is also something that we intend to work very closely with industry partners in the next few years. Next slide, please. So just to conclude, this century belongs to natural gas. I'm not sure how much hydrogen is going to come into play, but I am also an optimistic guy. But definitely this century is going to belong to natural gas. There is an expected increase in LNG global demand. So that means cold energy utilization or the cold economy is going to play a key role in the overall energy mix. There is a potential to utilize LNG, cold energy, for a number of technologies. I presented one such technology, which is using hydrate-based processes for both desalination as well as data center cooling and district cooling systems. We are open to international research collaboration. Before I end my last slide, I would like to extend my thanks. Can you go to the last slide? To all our sponsors. Without them, we don't get the chance to try our crazy ideas. This particular presentation, the funds have mainly come from Energy Market Authority, IMDA, and our industry partners, Shell and Keppel Data Centers. With that, I would like to close my presentation. Thank you, everyone.
Thank you very much, Professor Linga. This is excellent presentation. Let's have 2 more presentations on this theme before we go to the questions. And I would like to call upon Raj Naralasetti from Surbana, Jurong. Dr. Naralasetti, are you with us?
I saw him.
Excellent, excellent. Can you show your presentations?
Yeah, I'm coming up 1 second.
Thank you very much. Yeah, looking good. Perfect.
So, are you able to see it?
We see it and we hear you well. There we go. Thank you very much.
Okay. Good morning for folks who has joined from Norway, and good afternoon for the team who has joined from Singapore side. So I will just start. I think thanks, Praveen. You have covered something on the market side as well. I will start with the market, how the global outlook is for especially for LNG and gas markets. So this graph shows how the each type of energy sources or the fuel type is going to grow. The brown one, which you are seeing, is an oil one, which is expected to grow at a rate of 0.2% over next 30 years. And then natural gas one is the blue one, which you can see here. This one will run for this will be increasing at the rate of 1.1%. And we all agree that coal is a fuel which is going down, and remaining fuels like hydro, nuclear are pretty stable. And you can see that there is a big spike from renewables, which is 5.5%. But again, renewables need to be supported with energy storage systems. So this is how it is going to look like for next 20-30 years. From that previous chart, you can see that LNG is going to play a very key and critical role in the global supply of energy. So you can see that major players in the LNG like Shell, BP, and some of the consultants like McKinsey and IEA, they are predicting the rise of LNG between 3 to 4%. So on to the right, you can see the how the global demand has shrunk from the pre-COVID state to the post-COVID state. The dotted one, is basically the predicted for the pre-COVID state, and this strong line is looking at post-COVID state. Okay. So LNG demand grows from 359 mmtpa. The 359 mmtpa is a capacity which is in 2019, and it has grown. It has grown beyond 400 mmtpa from the liquefaction side in the supply, and there is already availability of 679 mtpa which is available, which can go from 359 mtpa to 679 mtpa in next 20 years. What it tells us is it is almost getting double. The demand is getting doubled, and the annual growth rate what we are looking at currently is around 3.1%. And the demand is shifting from the mature Northeast Asian markets to South and Southeast Asian markets. So you can see the table out here on the right side. So basically, the Southeast Asia is going to see a surge in increase in LNG, requirements. So which can go from 14% to 33% nearly. Whereas mainland China currently, which is at 17%, is going to increase marginally by next 20 years. Whereas you see Japan, Korea, and Taiwan, where they are already at a max capacity, is predicted to go down because of Japan shifting to nuclear and other sources of energy. And Europe is going to shift from 24% to 13%. This is mainly driven by renewables. Basically, they have got an abundant renewables. North America definitely became as a net exporter, so it has a very little impact on LNG industry currently. It will be more like a supplier. So this sheet tells you, this graph tells you where the major suppliers are. You can see that Qatar is number one, and then this is not an updated. This is a 2019 one. So Australia also increased its volume almost pretty much, very near to Qatar. And then you can see that there is Russia, which is also supplying quite a significant amount of volumes, and then USA. So on the user side or the receiving side, you can see Japan imports quite a significant amount of LNG, followed by South Korea, and then China, and then Taiwan, and Spain, and also India. So let us see what is LNG. I think most of us know that it is a liquefied natural gas, and let us understand what the cold energy is. When methane is cooled to minus 162 degrees C, that is where the volume of LNG, volume of methane shrinks by 600%, and we call this as a liquefied natural gas. This LNG has got two forms of energy. One, we call it as thermal energy, which is basically cold energy, and the second one is an expansion energy, the energy that is generated while it is expanding 600 times. So let us see why the cold energy is important, right? So as the energy consumption is increasing, the CO2 emissions are increasing in the world. So you can see that the at the liquefaction side, these plants put a lot of energy to liquefy natural gas to LNG, and such a huge LNG cold energy is transported via ships to various parts of the world. So today, by 2020, the world CO2 emissions are somewhere around 43 billion tons per year, which is quite significant. So although most of these countries have developed, greener initiatives, but impacts due to coal conservation are largely ignored. The reason why they are largely ignored is people feel that cold energy harnessing is always an expensive affair. But again, as if we are able to plan it properly, probably we can achieve the right economics to make it work for various applications. So in terms of Singapore, if you see that Singapore energy mix currently energy markets for the power generation side, 95% of the fuel comes from natural gas. So it's quite reliant on natural gas, and Singapore gets natural gas via piped supply from other countries as well as import from LNG. Singapore has also got that carbon tax regime, it started in February 2018, and currently they charge around $5 per ton, and which is going to increase to $10 to $15 per ton by 2030. So some of the major contributors for this CO2 generation is power plants, which are major. Then we have semiconductors, we have petrochemicals, and we have refineries. I did not put one more thing out here is even the ships, because Singapore is also a shipping hub. So as a SJ, we are looking at various, for developing a low carbon district where we can reduce that, carbon footprint using clean fuels, and also achieving this, lowering the carbon footprint by even from the energy optimization process. So typically the LNG, whatever we get, we can, some of our colleagues have already explained, the regasification, where we can extract the coal available while it is regasifying from LNG liquid state to gas. And that can be stored in cold energy storage systems, or it can also be, we call it as a cold batteries. And then we can also generate, utilizing that coal, we can also generate the cryogenic power, which is a very green power, and it is 100% green power. This technology works on expansion, which Praveen has already said, like ORC, where Japanese terminals like Osaka Gas has already been, operating that for last 20-30 years. And then the CCGT, whatever is the heat that is liberated from CCGT, we can utilize that to generate the chilled water. Then we can have a different networks like heating network, cold network, and a power network, and also a gas network. Gas network is basically whatever the regasified gas is there, you can directly pump in as a gas network. And then you can also have a district cooling network. So some of the major applications for this type of solutions is LNG terminals, data centers, or we can also, put up into the commercial buildings or even hospitals, ports, industrial parks, and also, built in environment. From SJ's perspective, we do a lot of planning jobs. We are also looking at, bringing such solutions well ahead at the planning stage, so that such solutions can leverage, optimization of the energy even at the planning stage. So we have an SJ-NTU corporate lab, which is at NTU, And the main purpose of this is to develop sustainable solutions to address the industrial challenges, leveraging on SJ's industry experience in urban and infrastructure areas, sectors, and also, bring in some of the good, world-class research capabilities from NTU side as well. So this is one of the corporate lab where, we invested quite a lot of money along with NRF and also, with the support from NTU. So this is one of the, cryopolygen, which is a polygeneration system, which will be tested, what Alessandro has already said, which we are planning to test this system. In this system, we are going to have an LNG, stored at, underground, and then we will be pumping the LNG and regasifying it. And the cold, whatever is harnessed, can be utilized either for direct cooling, which is for ACMB or HVAC purposes, or for freezing. I heard that somebody is interested to also grow salmon. Or also, you can also use that coal, depending upon the availability of the coal, we can also generate, cryo power generation. Apart from that, Alessandro's team is also working in, developing the thermal energy storage, which is a cold battery, which can be deployable both for the cars, buses, or even for the houses. So we are looking at these technologies where we use phase change materials to see so that we can export high grade coal, and we can also export quite significant amount of coal in one go. And downstream, as you all are aware, downstream we are also looking at a chilled water, district cooling system, and steam and hot water generation along with the power. So we would also like to take this as an opportunity to also connect our system to a gas grid where it can also send this gas to the household facilities. So what it means is it's a one-stop solution for the entire urban areas where this can act as a small microgrid. So we are going to test around 3.5 megawatts, power capacity of the gas turbine, and the cooling capacity we are anticipating is around 10 megawatts. So where such solutions can be deployed is for data centers, even for refrigerated warehouses, even for the airports. To make them green further, and then power plants, indoor farming. Also, we can also do that for built environment where in a major commercial buildings, or even for the hospitals, seaports, and also like what Praveen has already covered on desalination units as well. What are the key challenges? We foresee that there is a collaborations required from various industry partners to reduce this carbon footprint. So we all should all believe that this is one of our, motive to come together. And then second one is, I think there is a need for the coordinated efforts between the government agencies, regulators, to promote the development of such ecosystem. And always, it is always better to plan ahead so that such ecosystem can be developed well in advance. And there may be changes to the additional, there may be changes required for the safety and security measures because, especially in Singapore, we are limited with LNG trucks on roads. So, additional safety and security measures should come in place, to mitigate any such, incidents. Last one is, consultations with regulatory bodies on road safety and also cold export via trucks will help. One of the ways we can do is we can also, suggest a dedicated way for such trucks to move on. Is also one of the things which we can think through. Conclusion where this cold energy harnessing techniques will help is to reduce the carbon footprint. It also increases the synergy between the processes, companies, and the potential to attract like-minded businesses for greener solutions. It improves various process efficiencies, especially for the refineries, petchems, power plants, and all. Then it also helps in reduction of the operating costs. If you are able to do a proper planning ahead, especially at the conceptual design phase, we will be able to integrate quite a significant amount of businesses to the terminal operations without any disturbance to both the parties. So participation from regulators and also government agencies is required for such a successful implementation because there may be some of the things to be in place, especially there may be some regulatory changes required to achieve that seamlessly. Yeah, thanks, Per, for inviting me for this, presentation.
No, thanks to you, Raj, for giving us this. This is a really, really interesting presentation. Thanks a lot. Professor Gundersen, you're next. And I remember that Prof. Linga said that he had this crazy idea about using coal from LNG for CCS, for carbon capture and storage. And I believe that is the title of your presentation, isn't it?
Yeah, I'm not having screen control.
You can have the screen control, can't you? Just take it.
Open share tray.
Share content up. If not, I can see if I can find your presentation here and show it for you. Do you have it? Do you want me to show the
open share tray, but nothing happens? Somebody else sharing the screen?
I had the same problem, Per, actually. That's why I was not able to share.
Okay. Let me see. I can show it then for you. Just hold on a second. I will put it here and there, and then sharing. Sorry for that, everybody.
This has worked a number of times, so I don't understand why.
Yeah. It's the magic of technology, I guess.
Yeah. It's
Okay, can you see it?
Yeah.
Are we good? Okay, so I will just click for you then, Professor Gundersen.
Yeah, thanks a lot. I'll do my timing. So let me start by saying I'm very glad that we finally could have this Science Week that we originally planned for Singapore in April. As you indicated, Per, this presentation has focused on carbon capture in power plants by utilizing LNG cold energy. Power plants are responsible for 37% of global GHG emissions. Next slide, please. So at this point, I would like to acknowledge the great contributions of 3 of my previous postdocs, Chao Fu and Dong-Hoi Kim, that are with SINTEF Energy Research in Trondheim, and Hao Shui Yu with MIT Energy Initiative in Boston. Next slide, please. So, as already indicated, the presentation will be on power production with carbon capture, thanks to Alessandro, who introduced the Alm cycle. That makes life easier for me, and I will focus on the utilization of LNG cold energy. Next, please. We actually started looking at these kind of problems more than 10 years ago in a concept where we produced LNG from stranded gas offshore and used it in a power plant based on oxycombustion and with carbon capture through liquefaction. Next slide, please. So if you look at the last 10-15 years, there's been extensive research on oxycombustion-based power production. The IEA GHG has a report from 2015 studying 4 of these cases, and I will give a brief comparison here. Next slide, please. So there are 4 cycles. The first is semi-closed oxycombustion combined cycle. Next slide, please. I will not go into the details here. Clean energy systems has a Rankine cycle-based concept. Next slide, please. And then we have the modified S-GRAS cycle, which is a combination of a Brighton and Rankine cycle. And then as the 4th, next slide, please. We have the Alm cycle that was introduced by Alessandro in his presentation, which is a Brighton cycle. Next slide, please. So the performance comparison, we are comparing here with the reference natural gas combined cycle plant without CO2 capture. So you see that 3 of these cycles have a penalty for capturing, which is around 10%. The LM cycle, however, stands out as superior to the other ones with much smaller capture penalty. Next slide, please. So the Alm cycle is not very old. It was presented for the first time in Kyoto in 2012. There is a test facility in Texas that started up in May 2018, and they collaborate with Toshiba and Heatrick on turbine development and heat exchanger development, given the material challenges we have due to the operating conditions. Now, an important thing to say is that the Alm cycle is a recuperated Brighton cycle, and it uses supercritical CO2 as the working fluid. Next slide, please. So this is a flow sheet. We can see that natural gas is coming in. It's being pressurized. That's zone 2 up in the right corner. The captured flue gas also need pressurization. That's zone 1. And since the Alm cycle operates at very high pressure and high temperature, and it uses combustion with oxygen only, there is a temperature control problem, as with all these kind of cycles. So we need a big recycle of flue gas, which is primarily CO2. So that is zone 3, pressurizing the recycled flue gas. So these 3 zones are subject to study whether we can utilize LNG cold energy. Next slide, please. So for a 60 ton per hour natural gas flow rate power station, we see the gross power output here. And you also see that there are 2 big consumers of compression work. That's the recycled flue gas, and it's the air separation unit. I'm going to start by looking at the recycled flue gas compression. Next slide, please. Okay, going back to thermodynamics, since that's what I'm teaching. So the question is, how can we reduce compression work? And the answer is, of course, that we can liquefy and then pressurize by pumping. This very simplified equation from thermodynamics tells us that since the specific volume of liquid is 2 to 3 orders of magnitude less than the specific volume of gas, there is considerable savings in work, and there is also which is OPEX, and also large savings in CAPEX. So the idea here, of course, is to regasify LNG and use that cold energy to liquefy the captured as well as the recycled flue gas. Next slide, please. So my previous postdoc now at MIT, Hao Shui-Yu, he actually studied and tried to improve the LM cycle. So we have looked at 4 different cases. As far as infrastructure is concerned, we are looking at a standalone plant where the only LNG available is the one that we are going to use as fuel for the power station. But we also look at the cogeneration case where we are having a plant which is close to an LNG terminal. So we can act as the regasifying unit for the LNG terminal and then provide both power to the grid from the power plant as well as natural gas to the pipeline. So we are also considering 2 types of integration methods. One is direct integration, where flue gas condensation is obtained by LNG evaporation. But we can also use an organic Rankine cycle between the condensation and evaporation processes, which is what we refer to as indirect integration. Next slide, please. Now, the key issue here is that we need to have a good matching between the flue gas condensation and the LNG regasification, and pressure of these 2 systems is a crucial parameter here. So this slide shows the condensation curves for, it says CO2 here, that's the flue gas, which is primarily CO2, and the evaporation curves in a temperature enthalpy diagram for the LNG. So we need to have these 2 pressures suitable to get a good match here. Next slide, please. So this is a very simplified flow sheet. First, I'm going to handle the standalone case. We have 2 cases, that's direct integration and indirect using an organic Rankine cycle. So as I said, the pressures are important here. So the outlet pressure from the pump, the feed pump, is one of the optimization variables. When we solve the optimization problem, however, it turns out that the optimal pressure is equal to the operating pressure for the LM cycle, that's 305 bar. That means that we do not need a natural gas compressor, but the downside is that regasifying at higher pressure gives us less cold energy, so we are not able to fully liquefy the captured flue gas, which then needs, in addition to pumping, some fraction of it also need compression. The ORC case is the same optimal pressure. Next slide, please. So moving to the cogeneration case, then we assume that we have a very large stream of LNG. The large fraction of it is pumped to 30 bar, is regasified, and then sent to pipeline. Then the smaller LNG stream that is going to be used as fuel in the LM cycle power plant is regasified by liquefaction of the captured CO2. In this case, we have also 2 alternative integration or using an ORC. Next slide, please. So these are the results. We are focusing on exergy efficiency and work consumption for these 4 cases. If we first look at the standalone case, we do not have enough cold energy available to consider all the zones, so only zones 1 and 2 are considered. And you see the savings are moderate, and the additional saving by using an organic Rankine cycle is quite low. So it doesn't really justify the investment in an organic Rankine cycle. So our conclusion is that for the standalone case, direct integration is the best alternative. If you go to the cogeneration case, we see huge savings in work consumption. And we also see that using an ORC really makes sense here. We go from 87 megawatt saved to 136 megawatt. In this case, of course, we also consider zone 3, which is the recycled flue gas that is used for temperature control. One surprising thing here is that the exergy, despite the savings in work, the exergy efficiencies go down. That may look confusing, but it has a simple explanation, and it is the fact that we are actually using cold energy from the LNG terminal. So this cold energy or exergy is actually spent in our plant. That's why the exergy efficiencies go down. However, the alternative, as has been mentioned by several speakers already, is that this cold energy is going into seawater. So compared to that, this is really a superior solution. Next slide, please. So the second big consumer of work is the air separation unit. Next slide, please. Now, this is the classical Linde coupled column concept that is actually ruling the industry today. We have studied how we can improve that. So next slide, please. My previous postdoc, Chua, he studied this process for 2 years, actually, and came up with a single column concept. Press the button, Per, because there is animation here. Just click next. Yeah, thank you. So it's a single column using distributed reboiling and heat pumping. So we have a patent on this, and it has also been published in industry. We have considerable savings with this concept. Next slide, please. We have also studied how we can integrate LNG cold energy into an air separation unit. This also has been the topic for today's presentations. So we actually used LNG for pre-cooling purposes in the air separation unit. Next slide, please. So here's a comparison. We are not focusing on energy here, we focus on product quality. So compared to the single column ASU that we just had on the previous slide, when we use cold energy for pre-cooling, it means that we can actually deliver liquid oxygen rather than vapor oxygen. And the liquid nitrogen is almost 4 times the case for the single column air separation unit. And the exergy efficiency in this case is considerably improved. Next slide, please. So I'm going to end up by making or hinting to 2 cases where we are using organic Rankine cycle and where LNG regasification is acting as the heat sink. The first slide here shows how this can be organized. I mean, you can do all kinds of arrangements here with cascaded systems, etc. But this is the kind of main principle where you have an organic Rankine cycle between seawater as the hot or the heat sink, sorry, the heat source, and the LNG regasification as the heat sink. Next slide, please. We have also used organic Rankine cycles to produce power from gasifying LNG. In this case, we're using 3 organic Rankine cycles. And there is one additional item here that we didn't have. That is, we actually have CO2 coming in from the right here and being liquefied by exchanging heat with these organic Rankine cycles. So next slide, please. So to conclude, I think that this presentation, as well as previous presentations, has clearly indicated that cold energy, or exergy I like to call it, from LNG regasification is an important asset in energy efficiency, and it has numerous applications. It has also been already described by the previous speakers. So with that, I would like to end my presentation and hand it over to Per. Thank you.
Thank you very much, Professor Gundersen, for that one. We are now ready to take questions, and I will again invite you to put your questions on the comment box or the chat channel, or just raise your hand for presentation. Actually, I want to come back to the question that was raised by Mr. Espen Johnsen earlier here, and actually I would like to call upon him to ask, because you, Espen, you are thinking about the concept of producing salmon or seafood on land, in land-based equipment in Singapore, and one of the major cost element is cooling water. So can I just ask you, for your plant, how much cool would you need? I mean, how much cooling water? What are the amount, and what would be the cost saving if you could have connected that with, for example, coal from LNG? Espen, you can take the word if you like.
Yeah, I tried to unmute. Can you hear me now?
Yeah, we can hear you.
Okay, yeah, thank you very much, Per Christer. It's been a great web session and a lot of interesting aspects to look at. So indeed, we have been working since the beginning of the year on feasibility and a concept select study for land-based aqua farming in Singapore. And of course, we've been planning mainly on using electricity for the cooling aspects of it. So what we need there is the water, and we talk about, it's a staircase of opportunity as we go forward, but the very first staircase is around 10,000 cubic meter of water that needs to be kept constantly cooled at 14 degrees. So of course, it's not all going to be ambient because this is recirculating. So, but if you think about the ambient temperature around 30 and 14 degrees, so it's a delta T of 15 degrees, more or less. So that's the first step, and then we have some future steps, assuming that this is all successful, that will bring up that need much higher. So initially, we have been thinking of using electricity for this one, and exactly how much will be used for cooling, I think we are talking in the order of 1 to 2 gigawatt hours per year of the electricity being used for cooling. As I said, we have only done the feasibility and concept select study, so we haven't been into the detailed design and know it exactly. But I think that's more or less for the very first step, the electricity demand that could be offset by using SLNG cold energy to offset it. Of course, listening to all this one, I also hear the interesting element of creating potable water from using the hydrate methodology. That seems like an also very interesting opportunity, because we do use quite a lot of water also throughout the year. And then, of course, the last thing is around the distance. So that's where the whole thing started off for me, is where to best place this one. So initially, we've been looking at placing the plant within one of Singapore Food Agency's agriculture parks, which is a bit perhaps too far away. We'll also look at Jurong town halls, which is also tendering industrial plants, which is a much closer location in Jalan Papan. And then, but of course, perhaps the best thing, and I have looked at the Google map on where SLNG is sitting and the area around it. There seems to be some good space around the SLNG. Perhaps that's the best place to put up a future plant.
The man who operated LNG is in a little bit.
Yes, so Raj, could you give him some advice?
Yeah, maybe. Praveen, I will take this if you don't mind.
Raj, yeah, go ahead.
I think, taking the coal from a terminal is not a simple task actually, because we also need to acknowledge one thing altogether, that terminal is a strategic asset where the availability and reliability of that system matters. But having said that, there are possibilities where we can actually harness coal. We are not saying that it is not impossible, but we studied all the we can study all the controls, what can be in place to ensure that that mitigation can be done. So coming back to Johnson's question, whether someone will buy a salmon which is grown next to an LNG terminal, I don't know that, but definitely salmon within a water, people will buy it. But again, that land has to be, decided by SFA, Singapore Food Agency, to demarcate for the food usage. Yeah. Because it is an industrial land currently, and that may not be possible from an regulatory purpose. But if Johnson can come up with some of the solutions where any natural gas release doesn't affect salmons, then then should be okay.
I don't think that's too much of an issue, and we can have a more detailed discussions later on. But the land-based that's the whole charm of the land-based, is that it's completely isolated from its environment. So it's fully as long, and I suppose SLNG also has its requirement not to release into the atmosphere. So as long as the atmosphere is good enough, then the actual the land-based RAS systems, they are fully insulated from the environment. So and it's a recirculating system. So I've been in lots of discussion with the SFA already, as well as with Jurong Town Hall, or Town Council. So I don't think the location is not, and the fact that it's next to the plant is not too much of an issue. I think. Yeah.
So
and
typically,
also, I make sure that we have contingencies, and you don't rely in a RAS system. You also don't rely uniquely on a single source of either energy or water or whatever. So you do have to have mitigating options there to make sure it's secure. It's too dangerous to just rely on a single solutions on everything. So those two I'm less worried about, to be frank. So to me, it's still very exciting.
Yeah. To answer to in one-liner for your question is theoretically it is possible actually, but we have to overcome a little bit, other the regulatory concerns, I guess. Yeah.
Sounds like an exciting opportunity that we should pursue. So let's connect Espen and Raj after this meeting as well. If you don't mind, to take this further.
Question in the crowd. I mean, in the chat box. There's a question by Leong Sitong. It's directed towards me. If I can take that.
Please go ahead, Prof.
The question is, how mature is the technology for using hydrates for carbon sequestration? Leong Sitong, I would recommend you to join us on Tuesday. Adam Usadi is in the crowd as well. He's among the audience as well. We're going to talk about some of the activities ongoing through SGEC. He might present it. And I'm going to touch upon some aspects of what potential is there for carbon dioxide sequestration in the form of hydrates in my talk. So let's save it for the Tuesday's surprise. Exactly. Sorry about that.
Sounds good. Professor Hafner, you raised your hand. Would you like to comment on this?
I just had a question. Sorry for maybe it was mentioned during the presentation, but how is this LNG terminal nowadays utilizing? They need gasification to put the gas into the pipelines, isn't it? Is that done by seawater?
Yes, it is done by open rack vaporizers, ORVs we call it. So it's basically with seawater. So what it means is whatever.
But then if you talk about this district cooling system with a 14-degree or 15-degree water, that would be a really low-hanging fruit to implement, to exchange the seawater with that loop and utilize megawatts of cooling.
But unfortunately, Armin, the problem out there is, the temperature, seawater intake temperature and outfall temperature, the delta T is not so low. So what it means is Singapore water temperature is quite warm, unlike any other places in the world. It is between 28 to 30. Yeah.
But if you look on Truls exergy analysis, you have a lot of potential until you reach that temperature level, and then you can do the final. If you need this higher temperature in your gas, you can utilize your existing heat exchangers to do the last part. The very, very first part, maybe 90% of the utilization can go towards the district cooling. Very low-hanging fruits. There are a lot of European projects focusing on this.
Yes, I agree. I totally agree. But the way the terminal is built is on a strategic purpose to ensure that the reliability is not hit. So
I would say it's more reliable if you implement also the district cooling system, because then you have two places to.
Yeah, agree.
That's why scale and speed becomes important. So in the overall slide, there is potential, no doubt. Me and Raj, outside of it, we have done a techno-economical analysis with Keppel, which we haven't released it out. It's still confidential, right, when he was in SLNG. So yes, the potential is there.
So I think beside the CO2 or carbon emission taxes, we should also have exergy taxes. If you do
I like
this
this.
kind of if you don't do the low-hanging fruits, it must appear in some of these Excel spaghettis. So the economic people who have no clue on thermodynamics can understand that this has at least a financial penalty.
So Professor Hafner, how many people that don't know thermodynamics will understand the terms exergy?
But Truls can explain it to them.
Exactly. Very well. Okay, but we move on. Professor Hafner, you are the last speaker. So if you could share, yeah, you are there. So please take the floor and present about implementation of supermarket refrigeration systems.
Thank you very much. Now we move completely on the way to the other side, and we are looking into refrigeration and how and why we can utilize CO2, which is maybe a little bit unusual to many of you. I will first go very briefly into the introduction to refrigeration from our point of view and see what these achievements are from these protocols. You have heard about the Montreal Protocol, the Kyoto Protocol, Kigali, and so on. And then why we should not spread HFCs, hydrofluorocarbons. That's the current refrigerants which we are using, and which are the alternatives. And then I give you some examples. And if you start, when did refrigeration start? It's approximately a little bit more than 100 years ago. Before that, on the left-hand side, you see Norway was the major exporter of ice towards the globe. That is also one reason why Norway has a fleet of shipping activities. It all started with export of ice. And then the first battle came when the mechanical refrigeration started to produce artificial ice. And the reason for doing this was they wanted to produce in Germany beer all year long. The problem with the beer production was they couldn't do it during the warm summer days and so on. That's why you have nowadays also still you have the different beers. The Belgian beers are brewed at higher temperatures than the German Pilsner and so on. But the refrigeration made it possible to make a good quality beer all year long. And it was the meat transport. These were the major factors of introducing mechanical refrigeration more than 100 years ago. And by that time, it was only natural working fluids. Some of them were less healthy, but CO2 and ammonia and hydrocarbons have been used. And then in the 1930s, the CFCs, the freons, were introduced by an American company. We all know the story about what went wrong then or what happened. I mean, they were heavily introduced and they had low working pressures compared to the others, and they had a very strong marketing. There was big business behind. And but the challenge was there was a huge consumption of this stuff, and it was released into the atmosphere, and it stays very long time in the atmosphere, and that's still the trouble we are facing today. And why is it important? Because we need also alternative solutions for the super greenhouse gases, the one we are talking about now, these current HFCs. And you see on the right-hand side, the climate impact of cooling sector is quite significant. There's a huge amount of refrigerant which goes out. Is approximately 2% of the global total emissions is only related to the refrigerants. And then in addition, of course, the energy consumptions to operate all these systems. So we need to find really solutions to at least eliminate the 2% and also make the systems more energy efficient. Coming to the protocols, you see in Montreal, the Montreal Protocol started in 1987, and you see the nice picture from a girl in Indonesia. By that time, she fixed the ozone hole with this carpet she sewed on the sky. Of course, we need other solutions. We need other solutions. But what was the good thing with the Montreal Protocol? It entered into force only after 2 years. This is the most successful international protocol ever, and the fastest introduction ever, because everybody understood this is an action we have to take. And by that time, it was only the ozone layer which was the focus. There was no focus on global warming. But however, it triggered the revival of natural working fluids. Our previous professor, Gustav Lorentzen, he triggered this to apply natural working fluids, and especially CO2, in mobile air conditioning and heat pumps. Why mobile air conditioning? Because by that time, the car fleet had specifically the highest emissions of CFC, of these ozone killers, because the systems were made very cheap, and recharging every year was quite the normal stuff. They used refrigerant, they didn't stay inside. So Gustav, he implemented this into some research here in our institute, and nowadays you can buy the first cars. After 20-25 years, you can buy some cars using CO2 as the refrigerant. Then the Kyoto Protocol came 1997. However, that took 7 years to get into force. Why? Because the big players didn't contribute. USA refused to join, and also China and India were not implemented. However, Greenpeace took it, and you see on the right-hand side, these kind of advertisement, a little bit fixed by Greenpeace, they triggered something in the market. So Coca-Cola and all the brands you see on the bottom, since that time they replaced all their HFC equipment, and now they do only the cooling all in these bottle coolers all around the world with natural working fluid. So it had something good, but it took a long time. And now focus is more and more on greenhouse gas emissions and global warming. That's why we have the Paris Agreement, the Kigali Amendment, to phase down the use of these high super greenhouse gases. But the Kigali Amendment now is a kind of tricky thing, because in the meantime the chemical industry, they have taken out another kind of fluids which they believe is their fourth generation, but the problem with this stuff, it's unsaturated HFCs, so they just gave it a new name, but it's exactly the same shit, to be honest. But it's not stable, so it stays much shorter in atmosphere, which is of course good for the engineer who solved that problem on global warming. But the decomposition products are very, very nasty and dangerous, and that's so it fixed the problem on greenhouse gas emissions. The values are very low, but all these byproducts is a big problem. But that's not the focus of these protocols. That's why they go under the radar. But we believe we should implement natural working fluids, because that's a really long-term solution. So, and on the other side, this new stuff is also flammable. That is, in this respect, dangerous, because if you have a natural working fluid like propane or hydrocarbon, at least you know what your decomposition products are. But in this case, this stuff contains fluorine, and it's really dangerous what happens if it starts to burn. So it's really poisonous, and very few ppm can make the difference if you survive or not. So that's why we have to take care of this and be aware. I give you an example. The US Army has tested this stuff. This stuff on the upper right-hand side is what you have in your car normally, if it's a little bit older car. And what we see here is the side view of a radiator or a condenser. They shoot the bullet through it just to see the previous stuff. See now there's a hole in that heat exchanger. It is released, nothing happened, it's not burning. And this stuff I show you now, that's the one you have in the modern new cars all around the world, which has not the global warming potential anymore, but you see what is called, if you have an accident with some impact, you see what happened, and this stuff burns, and it's very dangerous to be in the close to this fire. That's when you have an accident and the car starts burning. Please leave immediately. So it's very different, but this is very underreported. Nobody talks too much about this. And the second problem is, or the real problem is, we cannot do this kind of life cycle climate performances of these systems because we don't know the emissions related to the production of these more complicated fluids. So this is all secret by the company. So to make a good comparison is really not possible nowadays. And especially these degradation products are a big problem for the biosphere and the food chain, and humans and the others. And we have alternatives which are actually more energy efficient. So why should we go into this unsecure future? We believe that we should focus on natural working fluids, and we should have, this is really no risk if you go into this direction. And what are these working fluids? It's carbon dioxide, as we will focus today. These are products, for example, for hot water heat pumps. In Japan, you have more than 5 million of these heat pumps in all over Japan in the houses. A lot of commercial refrigeration, we will go into a supermarket, but also industry has a lot of CO2 refrigeration system nowadays. Ammonia has been since the old days an industrial refrigerant. It is still used many places all across the world. Hydrocarbons are coming in to replace most of these low pressure fluids now in residential units. You see them in China, India, all over. They're coming in. Light commercial we have seen is there is no question anymore. The bottle cooling stuff is going in this direction, and also all home appliances like fridges and freezers are using butane nowadays. So this is a picture of what is currently installed in CO2 supermarket systems. That means CO2 is the working fluid in all the installation in the supermarket, and you see we are approaching more than 30,000 units in Europe, and even Asia it takes off. American is coming, and America is coming, and so it's going in this direction. So whenever they find local manufacturers or local vendors able to implement these systems, they utilize it, the big chains nowadays, because they see that this is a long-term investment, and they even can save save electricity. Sorry. So some examples. I don't want to go too much into technical details, but what is the feature of this supermarket system is, beside the cooling of the food and the food stuff, you can also implement air conditioning and heating up of the shop, which is in some places important. In Norway, it's more the heating. In your place, it would be more the cooling. But even in Norway, you need some cooling. But the good thing is we can implement these functions into the system, and it's all in one, and which reduces the total cost of ownership for the supermarket owner, because they have only one guy to talk to, and the service gets easier and so on. These are just some examples how this can be done with some advanced technology, really make it energy efficient. And I will in a while I will show you some of the examples like this one. The system was installed in 2 years ago in the capital of Jordan, Amman, and they they leapfrogged from the old HCFC systems, which were ozone depleting, straight to CO2. They save 40,000 kilowatt hours a year on this single shop, and they avoid about 20 kilogram release of refrigerant, which is 35 metric tons of CO2 equivalent. This is only for an example for one shop. So it is possible to do this even in a hot area. This is another place in Portugal. Similar findings there. This system is running very well. It has all these functions which we talked about, air conditioning and everything, and it saves about 30,000 euro a year just by reducing the electricity consumption from the shop. And Another feature what we can do with these CO2 systems, as we said, in Japan, it's a typical heat pump in all houses, but if you enlarge it a little bit, you can implement a chiller function. So you can combine your heating and cooling demand, for example, in high performance buildings like hotels. So it's very easy to make chilled water, take it down from 12 to 7 degrees, and at the same time produce a 90-degree hot water for the showers and so on. So this is an application to come in Europe. More and more companies are able to build it, and they can outperform all the other systems when you do these integrated functions. And we do this also together with some in a program together with India. And even in India, they will now be able to build these kind of systems. We do it together and implement this in a school kitchen to help the Indian refrigeration people to understand how to do this, to make training, because training is very important to understand this new technology, how to do it. So we have this kind of examples around the world, helping the society in refrigeration heat pumps to understand and how to go on further. So in a very short take-home message, we can do the safety of the people is very important. If you have these new HFCs, I'm not sure if really safety is taken seriously. And if we just look on these global warming potential values of working fluids, that's not the whole picture. We have to look on the byproducts and all the other safety issues as well, and take the responsible choices there. And we have to inform the end users. The end user is the key. If he knows what he's really into, then he would choose something else, I'm pretty sure. And ammonia is still a very good option in many places. It can be handled safely globally. It's not a problem. Propane plays more and more role, replacing HFCs, as I said. And the examples I wanted to show you today was CO2 in some of the applications makes really sense. And what is important, what we try to do is training and knowledge transfer to enable people to go into this direction and find alternatives. And the problem in many places outside Europe is that the return of investment is hard, but we should have a World Bank, a multilateral fund, programs not supporting the chemical industry to spread these new fluids all over the world. They should give loans to end users to implement these kind of natural working fluid systems, and they can pay back the loan by the saving of the operating costs, the electricity they save. That would help a lot to boost these kind of systems all over the world. Thank you for listening, and I'm very happy if you have some questions.
Yes, thank you very much, Professor Hafner. Excellent. Questions to Professor Hafner, or actually to anyone during this
I have a question for Prof. Hafner.
Karimi, please.
Karimi, yes. Yeah. I think, thank you for your talk. I mean, it's very interesting to know that at least something is changing in the world. But yes. My question is the following. For this task, is it a simple replacement of fluid, or are there any scientific or innovative challenges involved in making this transition?
Yeah, it depends. If you talk about hydrocarbon implementation, the only issue is to take care of the flammability issue, to design the systems carefully. And on the other hand, it is, but this has to be done with the new fluids as well. So because these new working fluids, they're all flammable. So then why should we implement something which is in addition harmful to the environment? We can use hydrocarbon, propane or butane in the systems as well. With the awareness rising, how to do it, how to service, we can do nearly a transition one-to-one by looking into ignition sources. But there are so many standards and guidelines available nowadays, so it shouldn't be not a problem at all. So that is the technology on low pressure system, but the CO2 system is a high pressure system, so it needs full redesign, full engineering, and that takes time, but it is possible, as you can see how it is done in Europe and in America.
Thanks. So what is the reason why US is so resistant to change to some of these two technologies?
You can imagine where are the global manufacturers of these kind of working fluids? And if they use the Monday morning revenue just to promote their fluids, and they spend, let's say, $5,000 on an institute in Asia to convince professors that the PhD should not go on natural working fluid. They should test some of the properties of one of these cocktails they have invented.
Okay.
You see, then you can link up hundreds of PhD students in Asia for a piece of money, which is nothing for them, but you can really prevent very successfully that they go into alternatives.
Right. Thank you for your comment. Very insightful comment.
Yeah, very insightful and very outspoken, Professor Hafner, but very true. I think we are moving towards the end of this webinar, but I like to call upon Professor Karimi again to maybe sum up a bit or have some closing remarks.
Well, let me thank all of the speakers. We had very interesting talks, very insightful talks. I think we got an overview of both the hot side as well as the cold side of the energy integration puzzle, and that really helps. And we had very wonderful overviews of cold supply chain and innovative ideas from both Prof. Ernest Chua as well as Prof. Praveen Linga about possible generations, and the talk on LM cycle was very, very interesting as well. So I think it should give us a lot of food for thought, and also I think one of the purposes for this seminar and workshop week was to promote collaboration, and I hope that this gives us an opportunity to maybe connect further and explore some opportunities for collaboration. So thank you again very much, and thank you for organizing this, and thank you to all the speakers for agreeing to give good talk. Thank you.
Thank you very much, Professor Karimi. Professor Gundersen, as a co-chair, would you like to say a few words as well, or?
No, I'll just second what Karimi said. I think it's been a very interesting session, and for sure, I noticed there's a lot of scope for collaboration between Norway and Singapore in many of these areas.
Yeah.
Thank you.
Yeah, I see this clearly as well. So let's follow up on this one. Before we close the meeting, I'd just like to draw your attention to the next two webinars in this under this theme of decarbonization. We covered the opportunities laying in energy efficiency, utilization of cold energy on Tuesday. As Professor Linga mentioned, we will focus on the CCS or CCUS. Quite a dense and interesting program there as well. And on Wednesday next week, we will look at hydrogen value chain, both from a industry downstream point of view, a generic point of view, but also specifically into the maritime sector. So we'll split that Wednesday into two sub-topics, where the last part is the maritime sector. And the reason for that is probably the lowest hanging fruit, if I can use such a term, for collaboration between Norway and Singapore, both being much into the maritime sector and looking into options for decarbonization of the maritime sector, and where hydrogen or maybe other hydrogen carriers such as ammonia is definitely on the agenda. So I invite you all to Tuesday and Wednesday, and with that I will thank to the co-host of this, or co-chairs of this session, Professor Truls Gundersen from NTNU in Norway and Professor Iftekar Karimi of NUS in Singapore, and I wish you a good weekend to all participants and speakers. Thank you very much.
Thank you. Bye.
Thank you, Professor. Thank you. Bye, everybody. Bye.